warm welcome to TecKXpert webinar on the topic of power quality and harmonics, causes, effects, and remedial solution. And this is a webinar which has been specifically organized for TNEB professionals on the request of Prabhakaran sir. And we are so glad that we could see so many professionals from TNEB join in here. The agenda for today is as follows. We will start with our founder's address, which will be continued by a keynote speech by Mr. Anil Kumar, who is a power quality expert on the topic of power quality and harmonics, which will be followed by question and answer session, vote of thanks, and the feedback session. So like Murugesan sir already told, TecKXpert was found with a single vision, and that is to organize the world's technology experts onto a single network to enable sharing of knowledge. And Murugesan sir founded TecKXpert in 2013 with this single vision. With this, I request Murugesan sir to give an opening comments and request Prabhakaran sir for giving the welcome note. Thank you.
Good evening, everyone. It is my privilege to welcome you all in this wonderful evening for this exclusive TecKXpert's masterclass session on harmonics. When Mr. Prabhakaran attended our TecKXpert's mastermind session earlier, he approached us to organize an exclusive session for TNEB engineers, and so we are here with today. The presenter, Mr. Anil Kumar, having more than 4 decades of experience in this subject, and he is a very apted person to handle this subject. His practical knowledge about this subject and the number of audits what he has done world over will give you, I'm sure that it will give you a lot of insights about harmonics. I'm sure we can organize more and more webinars like this in coming days. I have a request to all of the participants. Kindly take this knowledge, whatever you have learned from this webinar, to your down the line people also. Thanks to all participants. With this, I request Mr. Prabhakaran to take over and say few words. Over to you, Mr. Prabhakaran.
Anil Kumar sir, who is going to handle the session, and our dynamic Murugesan, the organizer and the moderator, and my dear friends and colleagues of TNEB family. This is a special session exclusively designed for TNEB engineers, as already pointed out by Mr. Murugesan. The reason is simple. TNEB engineers are traditionally accustomed to power equipments like transformers, breakers, etc., but not power electronics to that extent. Over the years, power electronics is seen as an allergy subject, if not by all engineers, but by some group of engineers like me. And harmonics is still more allergic. It is in fact a subject left by choice in our college days when we studied in engineering. But unfortunately, the subjects that were left by choice when we studied engineering have become more active and dominant in our actual practice. And in particular, in the last 10 years, in which IT innovation coupled with the power electronic devices like UPS, VFD drives are used everywhere, almost in all places where electricity is used. So it is in this context, this session is a small attempt to bridge the gap between the theory and practice. When I shared this suggestion to Mr. Murugesan, he was quick enough to concede the idea and arranged this webinar in a lightning speed. And I must thank him very much. And I also take this opportunity to thank my colleagues, Mr. John Sundarraj and Mrs. Jayanti, who have circulated the invitation in all WhatsApp groups in which they are members and motivated the group members to join the session. I request all the participants to have patience to listen to Mr. Anil Kumar sir and compile their questions and doubts, get them clarified at the end of the session. In fact, Mr. Anil Kumar sir, with a vast knowledge and experience under his belt, is known not only in taking the class interestingly, but also clearing the doubts interestingly, which will again supplement the knowledge sharing to all participants. I request all participants to feel free to interact at the end. And once again, I welcome you all and wish you all have a very quality time ahead. Thank you. Over to the moderator, Mr. Gupta.
So we now move on to the main topic, that is the keynote presentation on power quality and harmonics, focusing on the causes, effects, and remedial solutions. So a brief introduction of our keynote speaker today. Mr. Anil Kumar comes with a 40 years of rich experience in the field of low voltage and high voltage power systems, power quality, and automation. He started his career at Baba Atomic Research Center as a scientist and later worked for Tata Electric, ASEA, Voltas, and in various middle and senior level capacities at these companies. And his experience in power quality spans across 30 years. He has started since 1990. Maybe that's the time when people actually started talking about power quality. So Anil Kumar was involved in this field right from the beginning of the concept. And he has worked as an entrepreneur in the field of power quality and power electronics, associating with EPRI USA, Gossen Metrowatt Germany, Maris International Finland, specializing in the areas of power quality studies, power system analysis, harmonic modeling and simulation, real-time power quality monitoring, power quality data analytics and solutions, passive harmonic filters, active harmonic filters, hybrid filters, StatComs, SVCs, and energy storage systems. You name the field in the power systems, and Mr. Anil Kumar has worked extensively in that. So with this extensive experience, we are very glad that Anil Kumar accepted to be the keynote speaker for today's event. I will straight away move on to Mr. Anil Kumar to start the keynote presentation. Anil sir, it is all yours. Thank you.
Okay, thank you. Thank you all, and very good afternoon to all of you. Coming to your subject straight, I mean, already the introduction part is over. I know I'm addressing an audience from Tamil Nadu Electricity Board, I mean, all our power engineers. So I thought this presentation should have the taste of power systems and power engineering and the day-to-day, sort of work which power engineers deal with. So I tried to make this presentation in line with that need of the power system engineers. So now getting into this whole program of power quality, let's first look at the power system itself. I think since that will be the topic of interest, we take the power system first. I mean, when you say a power system, in the Indian context, the grid is all interconnected and each section has southern, northern, eastern, western load dispatch centers and regional centers. So the whole grid is interconnected, and so it is pretty complex. When the whole national grid is interconnected, it is complex to control. As we all know, electrical engineering in its alternating current form is not storable like water, gas, or data. So storing electricity is a challenge. So the stability of electrical grid is also maintained by frequency and voltage control. So to handle this complexity of the national grid, we finally go by controlling the frequency and voltage. That's a primary level control. Now, having said alternating current cannot be stored, yes, we can have technologies to do that. And the technology we do is either we store it in a battery, or we can store it in supercapacitors, or we can store it in the magnetic field of a coil. When I say magnetic field of a coil, by superconducting coils, by converting the alternate energy to direct current by power electronics. Then of course, but these technologies are still in its consumable stage, early stages. There are supercapacitors and lithium-ion batteries. All these technologies are in place, but to a large scale, to store AC is still a challenge. Of course, in the long run, these options of hydrogen are all coming up, so there will be more options of storing electricity. Now, when it comes to in its natural form of control, it's a double equilibrium when it comes to a power system. So when I say double equilibrium, if you look at the next slide, it says there's an active power equilibrium and there is a reactive power equilibrium. So when you say an active power equilibrium, we need to make sure that the active power generated at any moment should be equal to the active power consumed. That means, you have to maintain the frequency. That's where the frequency stability comes. If your active power and generated and consumed are equal, then your frequency remains at 50 hertz. As it changes, suddenly the frequency varies. On the reactive power side, how do you maintain the equilibrium? The reactive power is an extra load on the grid, as you all know. When the reactive power flows through the grid, naturally it gives rise to voltage drop. So that means when you want to do reactive, the objective of reactive power balancing is to maintain the voltage. So finally, I mean, as you all know, control the frequency. Yes, we have sometimes the spinning reserve available, and the transmission system operators calls the respective power generating station to, put that extra power required to stabilize the grid. But you all know that variable renewable energy sources like wind and solar cannot, participate in these situations, because your conventional power systems are all on a rotary inertia concept, but the variable renewable energy sources are all power electronics based, where the whole thing is dependent on your power generation output itself. So we can't expect a VRE source to participate in frequency control or the voltage control. So the next thing is, so that means that TSO can ask extra power generation from any of the states, as I said before. But indeed, for the active power equilibrium, the complete, we have to look at the active power equilibrium as the whole grid. For a larger grid, it is easy to maintain the equilibrium. Now, of course, in India, we are talking about the national grid and this concept. Now, if you look into how the analogy of an active power control works, as you can see, the network is connected or compared to an inflexible sheet. And now the inflexible sheet, that is the network, which is on one side pulled down by the load, and the other side is pulled up by the generator. So ultimately, if you look at this inflexible sheet, that is a network, you maintain at the 50 hertz by maintaining the position of that network by balancing between the generation and the load. Now, if you go to the reactive power, the scenario on the reactive power is something like this. A reactive power scenario, you will see that the reactive power needs are happening on the same sheet. I'm considering the same network as a flexible sheet. Now you can see wherever there is a load going up, you can see there is a need for reactive power correction there. So that means you can see the reactive power equilibrium of a grid can be represented by a flexible sheet with the reactive loads pulling it down, and the power station comprising compensating this force by pumping in reactive power there. So now how we do this? I mean, sometimes reactive power control, we can do it by locally. So the ultimate objective of reactive power correction is to pump in by capacitor banks, or we can use a static compensation system like a static VAR or STATCOM systems. So that is how we control the voltage. So ultimately, when it comes to the equilibrium on one side on active power, we maintain the frequency by generating power equal to the generation of the demand. And the equilibrium of the power has to be kept, by maintaining the frequency. And when it comes to the reactive power, we have to ensure that the required amount of reactive power is pumped in, so that the voltage is also kept on equilibrium. So now this is fundamentally a power system is all about. On one side, you have to maintain the frequency control by ensuring the reactive power, active power is balanced. And on the other side, we should take care of the voltage control at certain pockets where that inflexible sheet, as you saw in the previous slides, that flexible sheet. Sorry, I think there is some problem again. As I said before here, when it comes to reactive power, locally we try to compensate the reactive power where there is a need to pump in reactive power to stabilize voltage. So the whole concept of reactive power control to manage voltage, and the whole concept of controlling frequency by managing the power consumed and generated, maintaining equal, these are the grid is controlled. So now as you go into the Now, we will look into the concept of power quality now. As I said before, there we looked at a primary stage control where we are looking at the frequency control and the voltage control. Now, when it comes to power quality, I mean, power quality is a subject which is not addressed in the previous slides. Now, here, if you look into power quality, there are certain statistics in terms of the financial problem of a of a bad power quality. Some of these financial impacts, as it's seen in the slides, is that in the US, the study conducted by EPRA, Electric Power Research Institute, says that the PQ related losses was $120 billion per year. That is what the EPRA is study in the US. In the Europe, LPQA is another power quality initiative. When they have done a study on about 9 countries covering about 1,400 sites, they found the losses are about 150 billion. Now, the Indian context, when you have a Central Electricity Authority, one of their study was talking in terms of $3.128 million on account of power outages. I mean, it says 57% is due to sags and short interruptions, and 35% is due to transients and surges. Then there are again certain studies by Watsula in terms of the DG sets and inverters, batteries, which is used as an alternate source. Those investments are almost a lakh of crore. And the operational maintenance of that is another 30,000 crore. So in a rough estimate, 6% of the GDP is what is actually we lose in terms of power quality not being addressed correctly. So 6% of GDP is a lot of money. I mean, our country today struggles to meet the COVID budget. So we can imagine if we can ensure the power quality of the system is maintained, there is a lot of money the country can save. The good news is, of course, these problems are diagnosable and it is preventable. But the sad news is that the subject of power quality is fully misunderstood or ignored. Now, what is power quality? As we all know, when the power is generated in a generating station, we have a perfect voltage and a perfect frequency, 50 hertz frequency, and the generation voltage also as a magnitude, it is fixed. So you have a perfect sine wave. But then in an ideal condition, those sine wave concept is fine. But when this power, as we transmit through the grid, I mean, the grid has its own, effect on the power which is being transferred. So ultimately the waveforms, whether it is the voltage or the current waveform, it's get distorted. So a power system operating under ideal condition is expected to be perfectly balanced. However, in practical system, this ideal operational mode is not ever envisaged because the network components substantially affects the original sinusoidal waveform shape. Now, when it comes to power quality, there are different ways of characterizing the power quality problems. As you all know, power quality has two situations. One is certain power quality problems are very steady state, and there are certain power quality problems are non-steady state. That means, it comes and goes. It's a random behavior. So when it comes to the steady state, as you know, in a steady state, you can take under voltage, over voltage, or harmonics, or noises, DC offset. All these things are steady state variations in voltage or current. I mean, when it comes to under voltage, over voltage, this of course is on the voltage, but when it comes to harmonics, notching and DC offset and noises, this comes in the current. So these steady state variations are easy to capture and analyze, whereas non-steady state variations are at random. But the non-steady state, if you want to analyze what is non-steady state variations are, it's are either impulse or it is oscillatory transients, or it could be transient harmonics. When I say transient harmonics, sometimes you will have resonance happening in the network because at the end of the day, the network has capacitor banks, transformers, and the network also have its own natural frequency. So at the time of an impulse striking on the network can oscillate at that natural frequency. And sometimes if that natural frequency matches with the harmonics present in the network, it can create a transient over harmonic. So that is also transient harmonics rather. And it can, when I say transient harmonics, it reflects in terms of an over voltage on the grid. So non-steady state variations, is well explained. There are IEC and IEEE standards which explains how to characterize or how to interpret these steady state and non-steady state distortions. Now, IEEE 519, we all know it's a standard which connects the harmonics part. And the harmonics, of course, you see only in a waveform, whether it's a voltage waveform or it's a current waveform. It's a wave shape which is affected in when the harmonics are in the system. Now, when it is, when you have other type of power quality like IEC 61000, this case IEC 61000 looks at harmonics in terms of frequencies. For example, you can have low order, low frequency, high frequency, as well as electrostatic discharge. I mean, when it comes to the power quality issues. So that means when you look into power quality, when you're characterizing power quality, yes, it has steady state, it has non-steady state, and this is IEEE 519, which defines the harmonics part or the wave shape part. IEC 61000 looks into the frequency content of the power quality. When it's say an voltage or a current, it has a certain frequency content. Now, this frequency content in the harmonics range up to, let's say, up to about 200 order. That means about around 10 kilohertz or 9 kilohertz. We can say up to that level you can have harmonic currents. But as you go to the higher order, you will have more of noises, and it could again be either conducted type of electromagnetic phenomena, or sometimes as the frequency goes up, the cable will start radiating. So you'll have a radiated type of electromagnetic phenomena. So the frequency is another aspect of characterizing it. As I said before, the characterization of steady state and non-steady state, you can look into fundamentally as a voltage quality to start with. When I say voltage quality can be affected by switching transients, or it can also be affected by short duration or long duration voltage variation. So when I say switching transients, these are all caused due to lightning. Due to lightning, or sometimes capacitor bank switching also can create these transients. Sometimes the lightning can create an impulse transient. That means it will only have a single polarity. It will only be on the positive cycle. Sometimes an impulse can be on the negative cycle, but it will not be oscillating. But then a short duration voltage variation is like your voltage sag and swells, temporary short interruptions. These things can be short duration voltage variation. When it comes to long duration, under voltage, over voltage is all long duration variations on voltage quality. Now, we gain in voltage quality, we can have unbalance, we can have flickers, you can also have power frequency fluctuations. When it comes to waveform distortions, finally, when a grid is trying to maintain a good voltage quality, when you connect the load is going to create current quality problems, because the load is ultimately going to generate sometimes harmonics, or sometimes DC offset, or sometimes notching because of the type of power electronic devices you use. Sometimes noises. Again, power electronics works at very high frequencies, so it can create noises. So all these aspects you can see it on a waveform. Again, IEEE 1159, when you go into IEEE 1159, it classifies whatever I just told you, the voltage quality and current quality. Now, if you quickly look into this, the voltage quality has transients, the short duration variation, the long duration variation. And when it comes to transient, there are two types, impulsive and oscillatory. And if you look at the impulsive transient, you have again a very small nanosecond to millisecond. So when you say an impulse, you can see an impulse will have a sudden rise in voltage. So it will have a magnitude of spike, and it will take certain time duration to reach the spike and to drop to its steady state. So similarly, when you take an oscillation, when it comes to an oscillation, it has another aspect, which is the frequency. An impulse will have only a magnitude and the rate of rise of voltage, or the rate of rise, and the drooping. But when it comes to an oscillatory thing, it will also have a frequency over that. And again, these sort of fluctuations are all short duration. As you see, it's all in milliseconds or microseconds, so that it remains only in a half cycle or a quarter of your wave cycle, because your wave cycle is 20 milliseconds. So transients can be only in a half cycle or quarter of a cycle. Similarly, when it comes to short duration voltage variations, you have sag or swell or some interruptions. These things again remains only in short durations of the cycles. So transients and short duration variation we only call in terms of cycles. We don't talk in terms of seconds or minutes. And again, the sag and swell, for example, a sag is a drop in voltage. as we all know, plus minus 10% is the voltage we try to maintain. So if the voltage drops below 10%, let's say if it is at 70%, 80% for a period of few cycles, then we say it's a sag. A swell is like the voltage increase. Let's say it goes up by 20% rated voltage and it remains for a few cycles, then we call it as a swell. Interruption, as we all know, we are familiar in India, that either it could be short interruption or it could be a long interruption. Now, the long voltage variations are under voltage and over voltage. So under voltage, over voltage can last for minutes. Now, you are seeing transients and short durations are all either in microseconds or for few cycles of waveforms. But over voltage, under voltage can be there for a few minutes. So that's why we call it under long duration voltage variations. And then voltage unbalance, we all know RYB, if the phases are not balanced, you have voltage unbalances. Now, waveform distortion, as you have a load connected to the voltage grid, certainly it start drawing low current, and then depending on the type of load, if it is a power electronic load, or if it is a high frequency, or if it is a very dynamic load like a welding load or an arc furnace load, certainly it produces distortions in the current waveform. Now, current waveform distortions, power electronic device, you all know, produces a lot of harmonics, interharmonics, as well as it can sometimes be subharmonics. When I say subharmonic, it could be below the 50 cycles. Interharmonics are harmonics which are neither an odd or even harmonics. When I say odd harmonic, it is 3, 5, 7, 11. Even harmonics are 2nd, 4th, 6th, 8th. Interharmonics are in between these integer numbers. We call it non-integer numbers. Notching, as you know, in the voltage waveform, you can sometimes get notching when you are using power electronics, because when you use a rectifier, the rectifier will have 3 phases, and on each phase, when the conduction takes place through a diode, and when that conduction get transferred from one phase to the other phase, there's a temporary short circuit happens between the phases. That is how this notching happens. But the notching never goes to 0 voltage, because there is a resistance which always blocks the voltage to drop to 0. So current distortions or any current quality problems, we always see in terms of voltage distortion. And then again, other aspect is the voltage fluctuation and frequency variation. These voltage fluctuations and frequency variations are due to renewable energy sources, because when it comes to a solar or a wind farm, you can never be guaranteed about the voltage and frequency stability. These two things are ultimately, power output depends on the climatic conditions, the sunlight and the wind patterns. So that is why I took the initial slides to tell you that when it comes to voltage control and frequency control, if you have a varying source of voltage and frequency, then you have a problem that to control voltage and frequency, the grid operator ultimately cannot depend too much on a solar or a wind farm, because ultimately these generations are not going to sometimes contribute, at the speed and at the response time. Sometimes the grid has to be stabilized. Typically, power quality problems, generally, as I explained to you in the previous slides, we talked about short duration, long duration, steady state, non-steady state, harmonics. Now, when it comes to power quality, is a sum of all this. Now, voltage sags and swells are voltage quality problems. As you all know, voltage quality, sag and swells happens when you have a short circuit taking place. Certainly, there's a voltage sag which go through the grid, and ultimately a consumer gets affected. Similarly, a swell also, if a ground fault happens on one phase and the other 2 phases, there will be over voltage. So that comes as a swell. Similarly, if there's a sudden throwaway of load, you will also have a swell. So that means on the grid operation side, when you are handling, like capacitor switching, or when you have the load throwing away, or you have some new loads coming, or switching of loads, or when there is a lightning strike, all this can create these sags and swells or transients. Harmonics, as I just said before. Then the other power quality problem, which many times, so we blame it on harmonics, but the problem can be to do with the poor wiring and grounding. This is very common. Many electronic cards, sometimes when it fails, sometimes some of the manufacturing companies, if you contact them, they will say it's all harmonics. But the problem could be something to do with the wiring and part of it, because many times when you have a voltage sag or a swell or a harmonics in the network, the grounding, if it is not proper, these problems can get amplified. how it get amplified. For example, when you have a balanced network, and let's say you have a proper neutral. In a balanced network, the neutral has to be always at 0. But then when you have voltage sag or swell, or when there is a neutral point is which is getting affected. Now, as you know, when there is harmonics, okay, certain harmonics flow through the neutral. I will come into that subject later. But then when you have voltage sag or swell, if the neutral ground voltage goes up substantially, to do with improper wiring and grounding. So sometimes the problem can be due to wiring and grounding, but you may sometimes blame it on harmonics, which is not true. Capacitor switching is another power quality problem, as I just said before. Whenever you switch capacitor banks in any grid, naturally, it creates an oscillatory fluctuations, because a capacitor bank bring in certain amount of capacitance to the network, which is inductive. So that means that when that LC combinations are, connected, naturally there is a phenomena of natural frequency, and that frequency there's an oscillation. That's why when you do capacitor switching on light loads or full load, on all these conditions, you will have oscillatory transients going over the grid. Uh, the other parts are EMI, EMF, because today majority of the power electronic devices, it all produces a lot of electromagnetic interference. There are IEC standards which tells how much a power electronic device is supposed to pollute the grid or pollute the power system. How much these electronic devices should be immune. That means the EMI, EMF is very important in power quality, because many power electronic devices, if you just let it go loose, it can produce so much of power, harmonic or other electromagnetic emissions. And those emissions, sometimes the connected equipment in the grid may not be able to withstand. The immunity of those equipment may not be proper. That means EMI, EMF becomes another power quality problem. In most of the source of power quality problem, as I said before, one source can be lightning. It creates transients, sudden surge and in the grid. Similarly, switching operation in the grid, capacitor bank switching in substations. Then again, sometimes some industrial plants, when they have heavy loads or some ground faults, or a three-phase fault can create it. Sometimes branches of tree touching the power lines or some accidents can also create power related disturbances. And when it comes to other load related, the consumers who are connected to TNEB grid, you have a lot of power electronics like drives, VFDs, and lighting loads, those power electronic loads. Sometimes some of the consumer, when they switch on large motors, that can create a voltage fluctuation in your grid. Sometimes some people will be using dynamic loads like welding and arc furnaces. That again can cause fluctuations on the grid. So ultimately, it is the utility and the consumer and the manufacturer. The three people have to sort of coordinate each other to ensure the power quality problems are minimized. The manufacturers should ensure that the power electronic devices or whatever polluting devices they manufacture and supply to the user follows the relevant standards, so that it does not emit power, the sort of harmonics or other power related electromagnetic interference and all that. And those things should be immune also. Similarly, consumer should ensure that they have purchased the right type of equipment which does not cause all these problems. And the utility should ensure that, of course, the voltage quality is maintained. Now, when it comes to voltage quality maintaining, I know when the utilities are using capacitor banks, substation capacitor bank for switching, I have many customers who complained about their VFD has failed or UPS has failed because of capacitor bank switching. So the switching, when you say KVR or the size of the capacitor bank, and at what load you are doing the switching operation, and how many steps you have, all that affects the switching related frequency on the grid. So that is why sometimes the consumers get affected by those type of switching surges, and their electronic cards fail. There are various standards. I don't want to go into these things. There substantially IEEE and IEC has come out with many standards to define power quality. How do you measure power quality? What should be the immunity and emission levels of power quality? And what should be the sensitivity of power electronic devices to power quality problems? So what should be the type of electromagnetic interference, that is conducted and radiated electromagnetic interferences? How you should define that. IEC 61000 series at the bottom of the standard talks about those things. So that means this is a subject which is very wide in its nature, but it's all about basic concepts. standards are well defining how to understand these basic concepts and how to get the right equipment, how to operate the power system so that the power quality problems are minimized. Coming into a simple concept, I mean, I just talked about in the beginning about the grid operation part, and I also talked about the power quality, how it influences the grid. And now let us talk a little about the load part, I mean, or the network part. As you all know, any electrical load, we can always split into three parts. It will be resistive, capacitive, inductive. So whenever you do simulation studies or whenever you want to create an equivalent circuit, we always create that equivalent circuit in terms of resistance, capacitance, and inductance. Of course, the voltage and current, the effect of voltage and current on these three elements of network. Now, as you know, the Ohm's law, I mean, which says that any resistive load will have voltage and current going in its phase. So the IR, that the current drawn by a load, is the voltage applied divided by the resistance of the load. And the power equation is the Ri squared, or we can say U squared R divided by R. How do you calculate the power equation? Is when we know the voltage, the current drawn is V by R, to convert into power equation is V into I. So you can add V on the left side, so you get the power equation. In the both side of the thing you add V, you get the U squared by R. That is how the power equation is written. But directly taken, P is equal to V into I. And V, we know V is I is voltage by resistance. So that means V squared divided by R becomes the power equation. So the power equation you can apply very easily an inductive network or a capacitive network, and you can easily calculate what is the inductance value or a capacitance value. Here you can see, if somebody wants to know what is the inductance of a coil, when you know the kVr, you can take the kVr equals to voltage square divided by 2 pi FL. That is how we calculate that. Similarly, when it comes to capacitance, as you know, capacitance is inversely connected with the unlike resistance and inductance. So as when you take the equation, it becomes the current drawn by a capacitor is omega into capacitance into voltage applied. Similarly, the power equation becomes the kVr become omega, that is 2 pi f capacitance into square of the voltage. So sometimes if you want to find out, you have a capacitor of 25 kVr or a 50 kVr, and we want to suddenly find out what is the capacitance value, simple. I mean, 25 kVr divided by 2 pi f and the voltage of the, if you are a 440 volt capacitor, you can easily calculate the C value of the capacitor. In power factor correction, as we all know, the power factor, the concept of power factor comes whenever you have an inductive load connected to your power system. Now here, when you take an inductive load, let's say the inductive load is a motor, and the motor is fed from a transformer or a generator in terms of certain kVA. The motor takes certain amount of kilowatt to generate the work on the motor shaft. The motor shaft has to rotate at a certain speed and torque as determined by the load. So that means the kilowatt output, the active power available to perform the rotary motion of the shaft, that's the active power, which is kilowatt. The reactive power is where it is gone. It has gone into the motor magnetic field, because unless you create a magnetic field, you will not get a rotary force. So now the power which is gone and stored in the magnetic field is becoming your reactive power. So that means the total power consumed by a motor is a sum of active power and reactive power. So that means if you have a motor with a good power factor or an energy efficient motor, it will draw less reactive power. That means you can have your transformer or a generator less loaded by a motor load. As you all know, this is a fundamental equation how you calculate. It's a Pythagoras theorem. kVA is the square root of the kilowatt square plus kVr square. So the cosine or the phase angle between kilowatt and kVA is the displacement power factor, as we all know. That is calculated again by a simple formula. kVr by kilowatt is tan phi, and then you take the tan phi values, you get the kVrc, the reactive kVr required. The analogy is a simple analogy for reactive power is that a person who is pulling a load, as you can see, the load is horizontally moving on a direction. So the actual load, the power which is the active power used is to shift the load on a horizontal plane, and for that purpose, Mac has to lift the rope and pull it. So by doing that, certain amount of energy on the kVr, which is the shoulder to the shoulder height, and the horizontal distance the load is moving is the actual work produced by the pulling effect of the load. So now in a normal power factor correction, what we always do, we put a capacitor bank, and when you put a capacitor, certain amount of reactive power is exchanged by the capacitor to the motor. So how it works, the motor stores the magnetic field, energy is stored in the magnetic field. In the capacitor, energy is stored in the electrostatic field. So now between the magnetic field and the electric field, it does the exchange of energy. That is how the role of a capacitor, because ultimately electricity and magnetism try to handshake and they go together. So that means if you put a capacitor bank for a motor compensation, the motor from its electric field will exchange the energy to the magnetic field of the motor. So in the process, the exchange of energy taking place between magnetic field and the electric field of a capacitor, that is how we improve the power factor. As we see in the simple exercise is that if you have a load of 410 kilowatt, the load is, let's say it's at a power factor of 0.7. Now, as the power factor is improved by a capacitor bank, you can see as you improve the power factor to 0.95 from 0.7, you will see that the kVA is reduced by about 154 kVA. That means when you put a capacitor bank and improve the power factor, it reduces the kVA demand on the transformer or on the grid, and that is why we have to make sure the consumers are always maintaining good power factor so that the losses are reduced at the transformer side or at the grid side. So this particular basic thing of even for a consumer, if you are running some generators, certainly you can save that extra power on the generator or the extra power on the transformer so that you can connect additional loads by improving the power factor. There's another simple method. There's a table which everybody will be familiar. This table basically says that you all see it in manufacturer's catalog. For example, if you want to improve the power factor, let's say from 0.7 to let's say 0.95, the table tells you there's a multiplier of 0.66. That means this multiplier is the multiplier you have to use with the kilowatt to arrive at the kVR required. So if you have a 1000 kilowatt load, and in a 1000 kilowatt load, if you want to improve power factor from 0.7 to let's say 0.95, so that means 1000, you have 0.69. That means you have to put 690 kVR. That is how this table tells you. As you all know, improving power factor will have many benefits. It reduces the kVA demand on the transformer or on the grid, or even a consumer who are built on kVA basis. There is a kVA reduction, so there is a possibility of reducing electricity bill on that. Similarly, the kilowatt hour losses in the grid also substantially reduce, because a grid kilowatt hour activity, when you have a low power factor, naturally a lot of reactive energy is flowing through the transformer to the load. Now that much of reactive current that flows also adds up to the I squared R losses. So it increases the kilowatt hour losses. Now if you put a capacitor near to the motor, naturally the motor will, the capacitor near to the motor will exchange the energy from the capacitor electric field to the motor magnetic field and improve the power factor of the motor end. Thereby you can reduce the entire losses from transformer to the line. Similarly, the motor terminal, it can improve the voltage also, and it can improve the performance of the motor also. And low power factor means you will again get penalized. That means a high power factor eliminates the penalty charges, as we all know. It also reduces the investments required on the whole power system. You can reduce your transformer sizing, your cable sizing, all that you can reduce by improving your power factor. And as you all know, carbon emission is another aspect of global warming. So every kVR that you add into the power system, you can save about 100 kilogram of carbon dioxide emission from the power plant. Now, explaining a little about harmonics, as you all know, any power electronic device is a non-linear load. Now that means a linear load, as you always, we looked at the basic electrical load slides before. In a linear load, you have a perfect resistance, so there is no question of or a perfect capacitance or a perfect inductance. So the voltage and current behaves by a simple direct sine wave relationship. Either it could be lagging, leading, or it could be in phase. But when you have a non-linear load, certainly a non-linear load does not work like a normal linear load, because non-linear load, when you connect, for example, when you apply a voltage to a diode, which is a non-linear load, and you say, let's say we have a rectifier, the rectifier is connect, or the input side of the rectifier, let's say you are given AC input, and the rectifier output will have a DC battery storage, because ultimately in a variable frequency drive or in an SMPS, which is used for LED or any of these applications, you will have a rectifier and an inverter circuit. The rectifier circuit will be primarily diodes. So what happens, this diode will conduct when the voltage goes to its peak. So when the voltage is in its peak, like here, the diode will start conducting. When the voltage is in the negative peak, diode will conduct. That means you have a current flowing in the circuit as pulses. And that means this current is a non-linear current. There is no linearity between voltage and current in this equation. I mean, in this relationship. Then what happens? It produces a what we call a distorted current. Now, to explain a distorted current, the best way is look at a square wave. Now, if you have a square wave, by Fourier transformation, we can split the square wave into multiples of fundamental frequency. That means this square wave, let's say, is moving has a 50 cycle is the square wave frequency. Now you can have, based on the 50 cycle, you can have one fundamental sine wave. You can have multiples of fundamental sine waves. Now in this particular equation, we have a 50 cycle wave. Then you have a third harmonic, which is going like this. And then you also, the third harmonic is the I think the blue one is the fifth harmonic. So yeah, it's a combination of 3, 5 and fundamental, and plus a lot more other multiples of 50 cycles. So Fourier transformation basically tried to explain you that a square wave will have a certain quantity of sine waves of fundamental frequency, certain quantity. When I say quantity, magnitude. The sine wave will be, let's say, a fixed magnitude of I max. But when it comes to third harmonic, it will be I max divided by 3, the magnitude. Similarly, when it comes to fifth harmonic, it will be I max divided by 5. So here you can see, when you split any distorted waveform by Fourier transformation, it will be a multiples of fundamental wave plus the odd harmonics like 1, 3, 1, third harmonic, fifth harmonic. And this third and fifth means, third harmonic means 150 cycles, fifth harmonic means 250 cycles. And magnitude of the third harmonic and fifth harmonic or any other harmonic as you go up the scale will be 1 by third, 1 by 5, 1 by 7. That is why when you say higher the harmonics, lower the magnitude. That is how we always look at this harmonic waveforms. But now again, you have to see, I have to stress one more point here. This waveform, you see it as a periodic waveform. That means when you say periodic, the positive cycle and negative cycle remains the same, symmetrical shape, and it goes periodically in a waveform. So that is, and such periodic waveforms are created by full wave rectification. Now, if your rectifier is not a full wave rectifier, if it does a half wave rectification, then that will have even harmonics along with the odd harmonics. That means full rectification means it will only have odd harmonics. If it is half rectifier, it will have even harmonics also. Now, in normal conditions, if you are using a variable frequency drive, sometimes if you are noticing some even harmonics or anything at the input of the drive, that means the drive electronic is not working properly. Now, as you know, the various type of harmonics produced is by variable frequency. I mean, variable frequency drives is one source of harmonics. As you know, again, UPS is another source of harmonics. Then all your lighting, fluorescent lighting or your LED lighting also produces harmonics. Your computer equipment and all office computer and office equipment like printers, fax machines, all of them produces harmonics. Now, the basic equation, how you understand the type of harmonics produced by a device is defined by this characteristic harmonic equation. When it's a characteristic, as I said before, any of these three-phase or single-phase electronic loads are fundamentally doing full wave rectification. Now, if you go into a 6-pulse variable frequency drive that is conventionally used in a factory, the 6 pulse means it has 6 diodes in the circuit. That means when you have 6 diodes, you can see in the three-phase situation, it is 6 plus minus 1. That is how the harmonic, characteristic harmonic order numbers are generated. So you see this equation, if you go into a single-phase load has a, basically if you take an SMPS, it has 4 diodes. When it has 4 diodes, you have P become 4, and N if you take as number 1, that means P 4 plus minus 1 is 3. Then similarly, if N is becoming 2, then it is 5. So that means the single phase electronic loads start generating harmonics, characteristic harmonics, which are starting from 3, 5, 7, 9. when it is a even harmonics, I mean, when it is a three-phase load, it will start from 5, 7, 11. Now, these are all called characteristic harmonics. Now, non-characteristic harmonics are not defined by this equation. Non-characteristic harmonics are what? That is the even harmonics or in the inter harmonics or subharmonics. These are all non-characteristic harmonics. So that is why this equation is only used for characteristic harmonics, and any single phase or three-phase electronic loads, if it is working correctly, it is only supposed to generate characteristic harmonics, not non-characteristic harmonics. Now, again, if you look into the frequency spectrum of that, of the harmonics produced, because when you say a harmonics produced, it has two aspects. One is on a time domain, as the harmonic progresses as a time function, it'll have a magnitude, it keeps varying. And if you have third harmonic, it has certain magnitude. If it's a fifth, it has certain magnitude. And that based on time function from 0 to a cycle, it keeps varying. But now if you take it on a frequency domain, you can split it in terms of the frequencies that contains in that wave. Now, if you take a personal computer, since it's a single phase electronic load, it will start with the third harmonic current, 3, 5, 7, like that it goes on. Similarly, if you see electronic ballast, which is used in CFL, or if it is an LED, it starts again with 3, 5, 7 because it's a single phase electronic load. Magnetic ballast is not supposed to produce any harmonics, but sometimes if the core of the ballast gets saturated, it can draw some amount of 3 and 5 harmonic current. So sometimes as the aging takes place, the ballast also loses some of its linearity. So it can generate some amount of harmonics by the magnetic ballast also. Now, if you take a 6 pulse, a variable frequency drive, as I told you, here you have 6 diodes. Unlike in an SMPS, there are 4, here it is 6. So when you have 6 diodes, you can see that 6 plus minus 1 become 5. That means a variable frequency drive, which is a 3-phase UPS or 3-phase drives, will start producing harmonics from 5th onwards. So you can see here the 5th harmonic, 7th harmonic, like that it progresses. Now, if you use a 12 pulse drive, what happens in a 12 pulse drive? You don't have 5 and 7. You will see 11 and 13 is the starting harmonics because NP plus minus 1 starts at 11 and 13. Now, if you go for 18 pulse drive, you will only see 17 and 19 starting. Nothing from bottom will be there. If you go for a 24 pulse drive, you will have only 23 and 25 as the starting harmonic. So sometimes some of the manufacturers, I mean, consumers, they use 6 pulse. If it is producing harmonics, they may sometimes go for a 12 pulse, or they go for an 18 pulse, or they go for a 24 pulse. Also, of course, there are active front-end drives also. But I just want to warn you, when it comes to active front-end drives, see what is a VFD? A VFD is, it takes an AC input, it converts to a DC by a rectifier. Then that DC is converted to AC by an inverter, and the inverter generates the required voltage and frequency so that the connector motor will run at that required speed. So that is how an AC drive, conventional AC drive works. Now, if you go to active front end, what an active front end does is the inverter circuit that you already seen at the secondary or the conventional 6 pulse. The primary side also you have an inverter. So that means an active front end drive, instead of rectifier, they use inverter at the AC input side as well as at the motor output side. So we'll have 2 inverters coming in an active front end. But an active front end drive, what happens is it may not produce this 3, 5, 7 and all that. But then what it generally produces, it produces a lot of higher order harmonics. Because if you go for an active front end drive, none of these harmonics will be there. So everybody will be happy, oh, the active front end drives, I'm very happy not producing any harmonics. But active front end drive produces higher order harmonics. The higher order harmonics, sometimes if you go with a harmonic analyzer, which can measure only up to 50th order harmonic, naturally higher end order harmonics is not seen by the harmonic analyzer. So sometimes you will say active front end drive is not producing harmonics, but in reality, it is producing harmonic from 63rd and above. When I say 63rd, it will be at 3000 hertz, 4000 hertz, like that at that frequencies. But your harmonic analyzer, since it's only measuring up to 2500 hertz, it says there's no harmonic. So you have to be very careful when you say active front-end drives as a replacement for normal drives for reduction of harmonics. As I told you, this is a 12 pulse. As you see, 12 pulse, you can see in a 12 pulse, you don't have any other lower order harmonics. It only starts at 11 and 13 because of the equation 12 plus minus 1. So now in this slide, what it shows is that if you have a variable frequency drive, or if you have a different type of rectifier load. For example, a VFD produces the wave shape of a VFD. Current harmonic shape is something like this. That means it produces a 5, 7, 11, 13, and the total harmonic distortion by a VFD. This VFD is considered 44% because this VFD may have a line reactor at the input. Sometimes if you buy a VFD which does not have a line reactor or a DC choke, this 44% become 85%. So you need to make sure when you buy a VFD, if you want to ensure it should be below 40% and all that, then you should have an input line reactor or a DC choke. Now, when it comes to a conventional rectifier, which is again more or less same as a VFD, because rectifier is nothing but it converts AC to DC. So at the input of the AC side, you will see shape of wave is like this. It has 5, 7, 11, 13 harmonic. Similarly, if you take a computer, the wave shape is like pulses because it is, as I told you, whenever a voltage is applied to a diode, it conducts only at the peak of the voltage. So you will have pulses of currents. So this particular current, when you split it under Fourier transformation, you have 3, 5, 7 like that. A fluorescent lighting, and because the lighting itself, it has to produce a high voltage. The light, when it starts, you have to hit a high voltage to start, and then at the running mode, the voltage comes down. So if you measure the input side of the lighting, you will have a different type of wave shape as it is shown in this bottom. Now, when there is harmonics in the system, what happens is harmonics affects the power factor also. Now, earlier I said power factor is the phase angle between voltage and current. But if it is a perfect balanced network, yes, the perfect balanced network, your apparent power is √3 voltage into current. And if you want to see active powers, √3 into voltage into cos phi. That is how we calculate. If you want to calculate the reactive power, √3 voltage into current sin phi. This is how we calculate the apparent active and reactive power. Now, displacement power factor, that is a cosine of the phase angle between voltage and current, is a direct calculation. You divide apparent power by reactive power, you come to cos phi. Now, when you have distortions in the network, when there's harmonics in the network, you have a situation where the distortion adds up to certain amount of reactive power. That is called as distortion reactive power. So that means when you have a distortion, you can see your power factor comes down. The distortion reactive power is, in addition to your fundamental wave reactive power, the distortion wave, all the harmonic waves produces D square is the reactive power. We take the value like that. And then the power factor, you can see here, P square plus Q square per D square. Unlike the previous slide, it is only P square plus Q square. Here you have one D squared also got added. Because of that, you can see when there is harmonics, the power factor comes down. Now, when there is harmonics in the network, you can see the capacitance absorb the harmonics because the capacitor is 1 by 2 pi Fc. When I say 1 by 2 pi Fc, F is the frequency, and the higher the frequency, lower the capacity impedance. So you can see that when there is a harmonics in the network, because of this 1 by 2 pi Fc relationship, the capacitor becomes a sink for harmonics. It will start absorbing the harmonics because it becomes a low impedance path for harmonics. Now, if you put an inductance, you can see inductance is 2 pi Fn. That is how the inductive impedance is. That means higher the frequency, the higher the sort of voltage drop on the inductance. And inductance, by its natural behavior, it opposes the rate of change of current. That means when you have a high frequency current is coming into an inductor, its impedance goes up. So that means when you have a combination of inductance generated by your transmission line or your transformers and inductive motors, all that, it produces a certain amount of inductance. So that inductive impedance is proportional to the frequency. Now, if you have capacitors in the network, capacitor is inversely proportional. So now what happens, whenever you have an LC combination in a power system, if depending on what is the frequency that is in the network, okay, at 50 cycles, if you put capacitors, you will not see resonance because at 50 cycle, its capacitors are generally used to improve power factor at 50 cycles. You don't use capacitors to improve power factor at 250 cycles and 350 cycles because at those cycles, naturally, capacitor loses its property and it will start getting overloaded. So what you generally do, if you have a frequency relationship between the inductance and the capacitance, At the point where the inductive impedance and capacitive impedance become equal and opposite, you have a resonant frequency. So now explaining, if you look at the resonant frequency in a little more mathematical form, you can see the network when you have some capacitors, the network with capacitor along with the rest of the network. When I say source impedance, your source impedance means your generator source impedance, the transmission from the generator to your transformer, the transformer impedance, then the cable impedance from the transformer to your load, all that becomes your source impedance. Now in a conventional equivalent circuit, you will see the capacitance sitting in parallel to the rest of the inductive impedance. And if you have harmonic flowing from this VFD or a nonlinear load, at the point of resonance, these two become equal and opposite. Now the XL, XC, when it becomes equal and opposite, at the equivalent circuit, you will see at the denominator, you have a zero value. XL and XC becomes equal and opposite, denominator becomes zero. That means your current becomes infinity. So that is how when you say parallel resonance causes infinite current. But in reality, you don't get infinite current because the network has enough resistance to arrest the rise of current. So that way, or there is other impedances, leakage impedances, all that, which will not allow the current to go up substantially. So this is how the same which I told you before. In parallel resonance, what happens is you have two problems in parallel resonance. One is that your voltage goes up substantially and your current also goes up substantially. And that is how, because when the impedance goes up, for a fixed current source, you say harmonic current is generated by a VFD, that is a fixed current source. So that meant a fixed current source, when the Z goes to infinity, because when the equivalent circuit Z become infinity, naturally your voltage also goes up, because a fixed current source into the infinite impedance means infinite voltage. So in parallel resonance, you have two problems. The voltage goes up substantially in the grid, and the current drawn also goes up substantially. That is how the equipment failures and all those fire accidents all can happen at parallel resonance time. Now you should look at this. Now if you have a transformer of 1000 kVA, and if you are connecting a capacitor, let's say a 400 kVA capacitor to a transformer, and now you have an inductive load, you also have some AC DC rectifiers. That means if you have a nonlinear load in a network which is connected with capacitors and the variable and in linear load, then what we can see is when you have a capacitor of 400 kVA, this 400 kVA, there's a relationship, there's a mathematical relationship of what is the natural frequency of this network. The natural frequency of the network is calculated based on short circuit level, MVA, divided by the AVR. That is MVR here. So 16.6, if you have 1000 kVA transformer, divided by the percentage impedance, you will get the short circuit capacity. And short circuit capacity, you divide it by the kVR, the 0.4 MVR. It's all MVR relationship. So you get 322 is the natural frequency of this network. Now assume if you have a variable frequency drive producing fifth harmonic and seventh harmonic, what happens? The seventh harmonic will naturally get amplified. So that is what it is showing here. There's a seventh harmonic current is generated by a variable frequency drive. As you have seen, if you remember that Fourier transformation, I was telling you the magnitude of every harmonic will be a division of your fundamental current. Now, if fifth harmonic current will be 720 divided by 5. Seventh harmonic will be 720 divided by 7. So your fundamental seventh harmonic current in a normal situation will be around 100 amps. That means a 100 ampere current, that is a fifth harmonic current. When it flows through the network, what happens? Fifth harmonic current will give the impedance voltage drop on a equivalent to a fifth harmonic impedance. See what happens in a fundamental, when you take a 50 cycles, your impedance, everything is related to 50 cycles. When you take the frequency to the higher and higher order, naturally the impedance, the voltage drop on that impedance, also the impedance also goes up proportional to the frequency. Because as you know, 2 pi FL, the frequency is an important factor in deciding the impedance value, whether it's capacitance. So that means here, when there is a 100 ampere current, when there's a 100 ampere current, harmonic current is generated by this drive, if there is a resonance happening, then you can see there is a voltage, fifth harmonic voltage drop of 51.5, which is 12.7. So that means you can see this is a parallel resonance problem. So that means sometimes when you do harmonic measurement, if you see there is big harmonic voltage distortions or a harmonic current distortion, someday you should doubt the capacitors there must be causing parallel resonance with the impedance of the network because of the variable nonlinear load present in the network. There is also something called series resonance. The resonance can be two types. The series resonance, what you can see here is, in a parallel resonance, the source is all sitting on one network. In a series resonance, you can see the source of nonlinear load is elsewhere. That means if your factory is connected to a grid, and the grid is, let's say, having only linear loads. You have a motor, then you have fixed capacitors or automatic capacitors. Now, you will sometimes have this capacitor bank failing because of series resonance, because the grid is bringing harmonic current either from a neighboring factory, or the grid itself may have harmonics which will come here and cause a series resonance. That means whenever you put a capacitor network, you will either have a problem with a series resonance or a parallel resonance. In both situations, the end effect is same. Voltage goes up, current goes up, and accidents of fire happens. Now, as you can see, as you keep on adding more and more capacitors into the network, I showed you a little before, when you have 400 kVAr, your resonant frequency is somewhere around 322 is the natural frequency. Now, as you keep on putting more and more capacitor bank, you can see that the resonance point the natural frequency keeps coming down. If you put a 700 kVAr capacitor, then you have a natural frequency which is very close to fifth harmonic. It is at fifth harmonic itself. That means what happens, you will have a parallel resonance. So whenever you put capacitors in parallel with a transformer, you should always make sure that there is a problem with regard to parallel resonance. And now you can see in this equation how it affects the capacitor itself. When you have a capacitor, see a normal cylindrical capacitor, it is always manufactured and it has certain type of dielectric. These are all fixed with the capacitor itself. The series resistor is not the resistor which is put on the top of the capacitor. This is related to the inherent manufacturing aspect of the capacitor itself. So thermal resistor, series resistor come because there's a lot of link and all that we use inside. So certain amount of resistance are used inside the capacitor. So that resistor value will be very small. Similarly, thermal resistor is an equivalent computation based on the hotspot. This again is based on the manufacturer design itself. So typically a standard capacitor, you will see it has certain amount of losses. And if you go and touch the case of the capacitor, you will generally don't get any hot surface, because these resistance typically, around 0.5 watts or something like what we say in a capacitor loss per kVAr. So you generally don't get the capacitor casing that hot in normal situation. But now imagine your harmonics. Now the harmonics are flowing, naturally temperature goes. Now here you can see a distorted voltage waveform. A distorted waveform is there. And then you can see the temperature rises on the capacitor substantially. That means if you go and touch the casing, you will not be able to touch it, of course, because it will be more than 100 degrees. So that means here it is showing a conventional capacitor, which is not subjected to harmonics, is working with a normal temperature. But the moment capacitor is subjected to harmonics, you have a situation with regard to temperature rise on the capacitor. Now, how you protect the capacitor against this problem? You generally put a resistor. When you put a resistor, you put an inductor. And when you put an inductor, you are going to create a detuning of the capacitor. Now, this is generally what we do. We put a 7% or a 14% detuning reactor. But when you detune it, you are bringing a new frequency, a new natural frequency in the circuit. For example, if you put a 7% detune reactor, the natural frequency of the capacitor with the rest of the inductance become 189 hertz. You don't have a harmonic at 189 hertz. You will either have 150 hertz or 250 hertz, third harmonic or fifth harmonic. So 189 hertz does not cause any resonance. That is how we detune it and protect the capacitor bank against resonance. Now, if you have third harmonic current in the system, if third harmonic is 150 cycles, so you use a 14% reactor, and by using a 14% reactor, you are detuning the circuit away from the third harmonic current to 134. At 134 hertz, there's no harmonics present. So by detuning a capacitor bank, you are ensuring that the capacitor bank is protected. But only thing, when you detune, you have to always make sure the capacitor that you use should have sufficient voltage rating to take care of the detuning reactor. Because if you use a 7% detuned reactor, the capacitor voltage goes up almost by 10% because it is a vectorial sum. When you put a reactor with a capacitance series, at the capacitor terminal, the vector sum is that the capacitor terminal, the voltage goes up. Now, in a 7% reactor, you will have somewhere about a 7% rise in voltage. So, if you're using a 400 volt network, you have to make sure your capacitor bank is somewhere around 440 volt. Similarly, if you're using a 14% reactor, you have to make sure that your capacitor is somewhere about 480 volts. Now, again, your network does not have to remain steady at 415 volt. Your network voltage also keeps varying between 10% minus 10%. So that means you have to always ensure that also taken into account when you are designing the capacitor KVR in the low voltage. So that means in the low voltage, you either go with a 480 volt or a 525 volt in Indian context, depending on 7% or 14% we are using, because of the network voltage keep fluctuating. Now you can see when you put a detuning reactor, what you are doing is, for example, here you are putting a 4.4% detuning reactor. By putting that, you are making sure that the resonance point of the branch, the natural frequency or a resonant point of the capacitor reactor circuit is shifted between 3 and 5. So there is no resonance at that point. So by doing that, you are detuning capacitor to avoid parallel or series resonance. This is how the function of detuning comes into. As you all know, for IEEE 519, IEEE 519 defines what is the harmonic distortion permitted in terms of individual and voltage harmonic, as well as all the low voltage network. The latest IEEE 519 says that you can go up to 8% voltage distortion, but at an individual level, you can go only up to 5%. Now, if you go for higher than 400 volts, if you go to 66 kV or 11 kV, 33 kV and all that, you have an individual voltage distortion permitted is around 3%, but total voltage you can go up to 5%. This is IEEE 519. Now, if you go into current distortion, you can see current distortion, there is a limit. Current distortion you permit to a user. For example, if your network is not very stable, how do you say my network is, when I say a strong network or a weak network, if the short circuit level at the point of coupling, if it is very high, then we say the network is very stable. But if your short circuit level is low, then you say network is not very stable. And the short circuit level again is connected with the impedance. Here, what you are doing here is, if your network is stable and strong, then you can permit a consumer to inject up to 20% harmonic current distortion, because your short circuit level is very high. But in that point, if it is a weak, you are connected, a load is at a very long distance of a power line, where the voltage quality or stability is a problem, and where the short circuit level is very low, there you have to tell the consumer, sorry, I cannot permit you more than 5%. So current harmonic distortion goes by the short circuit level at the point where the consumer has connected is low. And depending on the short circuit level, either it is 20 times the load current or above 1000 times the load current, you can permit your consumer to go for higher distortion in current harmonic in this case. Now, I just I come to this point, probably, I don't know, since I cannot hear any of you, I'm pretty handicapped. So I wanted to make this session more interactive, but we had a bit bad start. So if there's any questions or anything here, maybe Shravan can call me on my phone and tell me whether should I continue like this or any questions, and I will take a hold here to answer some questions on whatever we covered so far.
Shravan?
Hello.
I
Okay,
think
okay,
you can continue.
Yes, sir. I've informed him.
I think I can continue. I'll go to the next. I hope whatever I so far covered could be easily comprehended, because I was going on a little fast speed also. Unfortunately, because of all this connection problem, I feel very disappointed that I couldn't go at the way I originally planned. But since it's a one-way communication, I can only express my views. Later, I can probably get the feedback on the phone. Now, up to this portion of harmonics, what I was trying to cover was that number one, I initially, hello? Okay. Okay, at the end, okay, maybe the slideshow is over after that, no? Yeah. I just want to summarize in brief terms whatever I discussed so far. Fundamentally, I started by talking about the necessity of frequency control and voltage control in the grid. And the frequency control, as you know, has to be compensated by generating active power. That means you have to make sure that the active power is balanced with the generation and consumption at any given point so that the frequency is maintained. Similarly, when it comes to voltage control, is done by reactive power, because ultimately reactive power flow, you don't want reactive power flow to happen through the entire grid. So you try to do reactive power correction locally at near to the load or at substations. Now you generally do capacitor banks to do this reactive power correction at the substations, or you ask the consumers to install reactive power compensation at their factory. Now by doing that, the voltage control is done. And as you see the concept, I was bringing an analogy of a rubber sheet. If it is a flexible rubber sheet where there is some sags that's happening, there you put, that is how we're trying to show that in the earlier slide. So you put a reactive power compensation there. But many times reactive power compensation, when we do it by conventional manual switch capacitor bank, what happens is, as I was saying in the earlier slides, it can create oscillatory transients, because certainly when you put a substation capacitor banks, certain MVA or 11 kV or 33 kV, you're trying to manually control it. But in real scenario, your voltage correction, if you can do on real-time basis, that is where static compensation or static VAR compensators are used. In those scenarios, we are able to respond to the requirement of power factor correction in every cycle. That every cycle is 20 milliseconds. That means cycle to cycle we are able to correct. So when you are trying to do manual switching of power factor correction, whether it is high voltage or low voltage, certainly it has to create some oscillatory waveforms, voltage waveforms, because it is disconnecting the flow of reactive power depending on the load requirement. So it is not a continuous smooth control like a static compensator or a static VAR compensator. So later on, I was talking about the basic loads. The impedance is nothing but capacitors, inductance, and resistance by simple Ohm's law. But when you go into the power equation, you can easily calculate the inductance value or capacitance value by a power equation. Then later on, I was talking about the power factor correction, the importance of power factor correction, and also the power factor correction means that when you add a capacitor, but generally it does is in the theoretical terms, the capacitor which is connected near to the load is injecting the reactive energy from its electric field to compensate the magnetic field energy. So ultimately, a power factor correction is nothing but exchange of energy between the magnetic field to the electrostatic field. So by doing this exchange by the capacitor with the inductors near to the load, we are trying to keep the grid away from the flow of reactive current and reduce the losses, whether it is a grid or in a factory network. So having said that, I said when you put capacitors, there's a possibility of resonance. Because any capacitor, when it works with an inductance, naturally the network will have a natural frequency. And if that natural frequency becomes closer to a harmonic frequency like 3, 5, 7, 11, then naturally that network can create resonance. It can be either a parallel resonance or a series resonance. A parallel resonance can happen inside a facility itself because your capacitor and your harmonic load, your transformer, everything in one place. But in a series resonance, you can have harmonic flowing from elsewhere and maybe at disturbing or destroying your plant. So and then there is IEEE standard that talks about how you define the harmonic voltage distortions. And when it comes to current distortion, the current distortion permitted is according to the fault level at a particular point. If the fault level is very high at a point, that means the network is strong enough to withstand higher harmonic current distortion. So according to the IEEE, the ISC by IL, that means higher the short circuit level, lower the impedance. That means if somebody injects harmonic currents, the voltage drop on the impedance will be lesser. That means your network voltage distortion also become lesser. That is why the ISI by IL concept is used in the IEEE 519. So that is the consolidation of whatever I just discussed before. And going to the next, When you use a capacitor, as I said just before, can cause over voltages. Now, whenever you, it's again, these over voltages can happen both at the time of closing and opening of a capacitor. Especially if your capacitor is feeding a network or a load, it can happen sometimes if the capacitor is overcompensating the load. For example, it is quite possible in a factory, you come across a situation where you have a 25 kVR 5 steps or a 50 kVR 5 steps. Now, if your load demand is only, let's say, 10 kVR, and if your minimum step is 25 kVR, what happens is 25 kVR will immediately try to switch off at a light load, and that can create a surge. So that means this scenario, whether it's a low voltage or high voltage, the surges are dependent on the loading of the network. You cannot connect a capacitor to a light load condition, because if you connect it to a light load condition, you will have these sort of oscillatory transients or voltages taking place. So that is what this slide is saying. Into the next, that means either you can control in a low voltage system. Sometimes these oscillations you can control by using thyristors, because conventional contactors takes a few seconds to switch on, because the contactor has its own time delay. But in a thyristor, your switching time is much faster. That means you are able to correct when you take a 20 millisecond cycle. In a 20 millisecond cycle, you cannot bring a contactor to switch on in 20 milliseconds. Even a thyristor cannot be to do it in 20 milliseconds, but at least about 60, 70 milliseconds in 2 or 3 cycles, delay only will happen with a thyristor. That means you are able to bring the power factor correction much faster than a contactor. Second thing is, if you look into whenever you connect a capacitor to the grid, if you look at in a voltage waveform, if the voltage waveform at the point, if you connect the capacitor at 0 volts, that means there won't be any current flowing into the capacitor. There won't be any surges. That means in a thyristor switching, you try to close it at 0 volt. When the voltage waveform is at 0 point, you try to switch on the capacitor bank. There is no inrush current, so you will not get a over voltage. Similarly, when it comes to switching off, now if you imagine your capacitor is already charged with some voltage. Now, if you can ensure that if you can switch it off at the current 0, then again there is no surge will happen. So that means switching on and off at voltage 0 and current 0, if you sequence it like that and do thyristor control, or even if your circuit breakers, if you are synchronizing these switching 0 crossover points, then you can avoid the over voltage caused by a capacitor bank even in a substation switching. And another major factor is the leading power factor, because a lot of today with power electronics being added left and right, unlike the past where everything was inductive loads, you only used to have lagging power factor problem. Today in the industry, you go wherever data centers full of computers, all computers are capacitive loads, LEDs are capacitive loads, VFDs are capacitive loads. When I say capacitive loads, all these loads uses a capacitor at the rectifier for creating a DC voltage. So it is fundamentally a capacitive load. That means all this capacity load, when you connect it to a grid, naturally it causes a leading power factor. And many times your capacitor bank becomes useless, because already a leading power factor, why you want to switch on capacitor bank there? So that the leading power factor problem is very common in conventional, when you go with this sort of load, which is substantially leading, and you put unnecessarily waste a lot of money on capacitors. And people, that means this is an area when it comes to leading power factor, you have to use the right type of technology. There are the solutions like smart hybrid filters, we call it. What a smart hybrid filter does is, a hybrid filter will have capacitors as well as active harmonic filter together in one network. And this capacitor bank and active harmonic filter are synchronized in such a way that the active harmonic filter will take a decision when to switch on capacitor, when not to switch on. For example, let's say you require, you have a capacitor bank of 25 kVR, 4 steps. Now, let us say the system requires 30 kVR. Now, what the active harmonic filter do? Active harmonic filter will bring the 25 kVR step first, and 5 kVR it will inject. Now, assume a case, the reactive power requirement has gone down to 20 kVR. Then what the active harmonic filter do? It will still maintain that 25 kVR capacitor on the nets, on the grid, and it will inject a lagging power factor, so that it will take it into 20 kVR. That means a capacitor bank with active harmonic filter can do this cycle to cycle correction of power factor on each 20 millisecond cycle on a real time basis. So that is the right solution to avoid the leading power factor problem. So the leading power factor problem, you can have an active harmonic filter with a capacitor bank together. Whenever you are lagging power factor problem, you bring in more capacitors. Whenever you are leading power factor problem, you bring the active harmonic filter and inject lagging power factor so that it remains steady at unity power factor all the time. So that is one way of compensating this leading power factor problem. If you don't, if you put a lot of leading power factor on a generator, as you know, in a generator typically 0.8 to 0.97 is the safe. I would say 0.8 unity is the safe operating region of a generator, alternator per se. And if you take the power factor leading more and more leading, then naturally the AVR will switch off and the motor generator become unstable. So this is a stability curve of an alternator. So typically there is a question asked by many people, can I put a capacitor bank parallel to generator? The answer is, if you are able to use real-time fast control, that means if you can use a hybrid active harmonic filter with a capacitor bank, you can parallelly connect this capacitor bank with active filter on a generator also. And by doing that, you can always run the generator near unity power factor and save energy of fuel consumption, everything can save on the generator. So, but if you put a contactor switch capacitor bank, there is a risk that the contactor switch capacitor bank may increase the power factor on the generator to leading beyond 0.97, and it can cause over voltage and trip. So that means if you ask me whether you can parallelly connect a capacitor bank with generators, sorry, if you can parallelly connect, sorry, there is a disruption. Yes, you can parallelly connect a capacitor bank to a generator, provided you have a good controller to control the reactive power correction. Now, when I say good controller, there is another aspect when it comes to controllers. There's something called a 4-quadrant operation. Now, it is quite possible in solar application. You have sometimes the solar plant is generating power and exporting to the grid, and some other time the plant is consuming power from the grid and the solar plant is not generating. So, or there's a combination of the two. The 4-quadrant operation basically, a power factor controller or any other active filter that you're using for correcting leading power factor, if you can do this 4-quadrant operation, the advantage is that whenever you are in quadrant 1, let's say when quadrant 1 happens is you are consuming power from the grid. I'm assuming I myself as a user, for example, I am consuming power from TNEB. When I'm in quadrant 1, what happens is I am drawing reactive power as well as real power from the grid. I have a certain amount of lagging power factor, certain amount of kilowatt I'm consuming. But when you go into the export mode, these two are export mode. You have a quadrant 3 operation, which is not very good, because in a quadrant 3, what happens is you create a leading power factor problem. I'm sure the TNEB or any utility that matter, if you have a solar plant, they won't allow me to inject leading power factor to the grid. So a 4-quadrant operation, function of a 4-quadrant operation is to ensure that the controller that you're using is safely ensuring that the solar plant is not exporting reactive power, or rather, if it is importing, let's say, sorry, I'm sorry about that. If it is importing, reactive, you are going to be penalized by TNEB. So you have to make sure this 4-quadrant operation is balanced correctly so that the regulatory requirements are met. On one side, if you are exporting power to the grid, yes, you should export both reactive power and active power to the grid. You cannot export active power and draw reactive power from the grid. That means TNEB can penalize the consumer. So you have to make sure that the controller works in 4-quadrant operation efficiently so that this flow of active power, reactive power is managed carefully. Now, having discussed all this, now whenever you have across a power quality issue, there is a methodology that one should follow for a power quality problem, because many times, many customers, that matter, even TNEB has, when you are giving power also, you sometimes connect some problems to harmonics. But many times, certain problems need not be harmonics. That means when you do a power quality methodology or a study, you have to make sure when you start the power quality study, the first thing is to identify the problem category. When I say problem category, the problem can be sometimes due to a bad earthing. It can create a neutral ground voltage and because of bad earthing. Or the problem can be due to a DC offset voltage. When I say DC offset voltage, there could be some variable frequency drive or saturated transformer which may be causing some DC offset. But sometimes you put a blame on the harmonics. So you have to always ensure that the problem is correctly identified instead of blaming it always on harmonics. So that means you have to look into this power quality criteria or the characterization of power quality, as I said at the beginning on IEEE 1159, and accordingly you have to use a instrument, a good power quality analyzer, at the areas where the problem is identified. That means problem characterization and identification of problem area will go together. Now you identify there's a power quality problem. Let's say it's a neutral ground voltage. So that means we have to see which area is the neutral ground voltage problem, and then you connect the analyzer and characterize the problem. When I say characterize the neutral ground voltage, that is basically you can capture the voltage waveform, you can take the magnitude, and you can decide the duration. So that is how you characterize. For example, if you want to harmonics, if you want to characterize, you look at what is the frequency, what is the magnitude, and what is the duration of that, whether it is odd harmonic, even harmonic. So that is how you characterize. You find out the cause and how it is impacting the equipment. So when you use a power quality analyzer, you should be able to identify the problem, you characterize the problem, yeah, and identify the areas the problems are there, and accordingly give a right solution. It is not that all power quality problems are harmonic problems and all power quality problems are solved by active harmonic filter. No, this is a normal trend. I know in industry many people sometimes do. If it's a transient problem and some electronic card fail, also somebody will say harmonic problem. Or it could be sometimes a noise signal, which is because a lot of electronic devices produces noises. And if your grounding is not proper, naturally these noises will pass through the ground and it can come towards the power side. And it can cause some failure of electronic cards because the reference voltage of the electronic card will get affected and the card will fail. But then sometimes people say it is harmonics. So this is where, so now you have to make sure correctly identify the problem, characterize the problem, define the areas where the problems happen, and then give a right solution. When you say right solution, economic evaluation you do and you give an optimal solution. This is how you should do the power quality methodology. Now we have certain analyzers, we can use it. The type of analyzer that you should use for power quality analysis, number one, it should be complying to class A, IEC 61004-30 class A. When I say class A, there are class B classes analyzers which are not according to the required standards. So if you are doing proper power quality study, as I explained before, you want to look at characterizing all type of power quality problem, starting from voltage, transient, surges, over voltage, under voltage, notching, interharmonics. If you want to analyze all this, then you have to go for a class A analyzer. And this is a typical analyzer which will have a screen, which will have a 4 voltage and current input. It can also communicate. That means you can have a GPS synchronizing. That means you can have multiple analysis done at multiple points and use synchronizing with GPS network so that all the time stamping is done correctly. So if you're doing a measurement, let's say in a factory, you can have multiple analyzers connected on a GPS network so that if an event happens, simultaneously all the analyzers will timestamp it at the same time. So that will give you a better analysis of the problem. Sometimes, you should also, when you do analysis, if there is a fault happens or if there is a unwanted power quality event, the analyzer should have to capture the pre-fault, during fault and post-fault waveforms. So if the waveforms are captured correctly, then you can do something called a waveform signature analysis. By doing the waveform signature analysis, you can exactly analyze what is the problem. For example, if you have an underground cable and if there is an incipient fault like an arc fault, the waveform voltage will tell you how that distortion is. So from that you can interpret. That is called waveform signature analysis. That means you should use power quality analysis which can also do waveform capture. When you say waveform capture, you should capture enough cycles in terms of pre-fault, during fault and post-fault. So using this sort of waveforms, you can correctly analyze what was the condition before the fault and during fault, how the system was behaving, and after the fault, how the system is behaved. So that sort of analysis is required. This is there is also something called fixed power quality monitors also you can use. You can install this fixed power quality monitors. This is a typical power quality monitor which you can install at the and do continuous power quality monitoring. Now this power quality monitoring, as you can see, it can have up to 16 channels. That means you can simultaneously monitor up to 3 feeders in a substation. You take the voltage module and take 3 current modules from a single feeder. You can monitor up to 3 feeders simultaneously in this meters. There are other power quality meters which can come with single feeders also. But then what happens is this sort of power quality meter. This is that power quality meter. This is a these sort of power quality meters, you can connect it with analog signals, digital signals. You can give CTPT input, and then you can remotely log it and all that. Now, this is all about continuous real-time power quality monitoring. I'm talking by fixed meters. The other one is using portable analyzers, but when you use fixed meters, we can always do waveform capture, waveform analysis. You can, before a fault happens, you will be able to find out there is a fault happening or something is aging. And for example, if an OLTC which is not working properly, you get to know OLTC failure only when the OLTC has failed. But if you have a recording happening through a PQ meter, from the waveform of the PQ meter, we can always see the voltage is, there is a distortion in the voltage. That means OLT is not functioning properly. So before the OLTC fails itself, we can find out the performance of the functioning of the OLTs by continuous waveform recording. There's also something called, this is a very important when it comes to grid level monitoring. There is something called a software PQ view, which I have been familiarized, and I've been doing these sort of projects abroad. This PQ view is a database software. What it does is, in the software, you can bring in data from your power quality monitors, your protection relays, your SCADA system, your revenue meters, and you can analyze all the data, and you can create the required reports or waveform analysis. For example, if an event takes place, the event data can be captured from the digital relays or from the PQ meter, and by doing this, you can relate power quality problem to any other event and relate it. That means all the data will be in one point. In a substation, if you install this, now let's say I will bring a typical example for that case. When you have these multiple devices, that particular case is, this is how the events are captured by the continuous event monitoring. I will bring to an interesting case here where these are all various type of events that is captured on the continuous monitoring. So this is a case where you can locate the fault by using continuous this sort of software. For example, when a fault happens, a fault on the screen, you can see the fault is, this is a waveform which is captured by the PQ meter, and now it's also displays in terms of event happen on an event list. You can see this is an event happen, and this is how the voltage waveform is. And now what happens is, then the software calculates the reactance to the fault, and then it matches the reactance to fault with the feeder model, and then you can visualize the fault. This is a feeder model, and you can visualize it on a Google map. That means if you have an underground cable or an overhead line, by using this continuous PQ monitoring, you can you can see it on a Google map where exactly the fault has taken place. By having this, what it does is, fundamentally, when a disturbance or a fault happens, let's say a fault has happened at this point, and what happens is, the PQ relay, the moment the fault happens, your breaker will trip, and when the breaker is tripping, the protection relay will know what is the cause of the trip, and your PQ meter would have already taken the pre-fault waveforms and the during fault waveforms also. That means the protection relay data, the breaker trip data, and the waveform data, the software will compute the fault to distance, and then also it looks at the resistance to fault. Then it compares this data with the network model. There could be a network model for your underground cable or overhead line, which is there, could be there in the operation team at TNEB. Then with the network model, this will compare, and on a Google map, with exactly, with an accuracy of maybe about 100 meters could be the accuracy level difference. But then what happens is, it's an artificial intelligence is there in this software. Over a period of time, the prediction become more and more accurate also. So this is how continuous recording of waveform, recording can be done, and continuous monitoring of power quality can be done. So with this, I concluded this presentation. So in this last few slides, I was basically explaining in terms of how capacitor bank can create overvoltage in the network, how leading power factor problems can happen, how generator should be stabilized against this the power factor problem by proper control, how to take care of this fourth quadrant operation by using proper control so that the export and import of power is correctly balanced in terms of the active power and reactive power flow. And when it comes to continuous monitoring of power quality, you can have either power quality monitors, fixed monitors, and use software and remotely, like this fault location monitoring and all that you can do remotely. Sometimes you can use this continuous monitoring and determine there is an incipient fault, like an underground fault is happening. Before the fault turns out into a fire or a short circuit, the waveforms can have that waveform shape by doing the waveform signature analysis, we can interpret, okay, there is an underground incipient fault happen at this particular distance. By doing that, you can avoid a major short circuit which is happening in underground. And you can also use right type of PQ analyzers, which is this class A certified analyzer, so that it can do all type of power quality study, a transient, sags, swells, harmonics, noises, rather than only concentrating on harmonics to find out the power quality problems. With this, I have concluded. I'm sorry that I couldn't interact with all of you in this session. Yes, I think we will see how to rectify this problem and future make it to work better. Hello.
Yeah, thank you, Anil sir, for a very interesting presentation. So what I'll do, because we are lacking the audio, or there is a technical glitch, I will request members to post their questions in the chat window. So if you can stop sharing and open the chat window, you can see a host of questions which are being posted there. So maybe you can go in the sequence and you can address those questions, sir.
Okay.
And I request the members to only post questions in the chat window. We can post the thank you, appreciation messages much later. For the interest of having a seamless interaction, kindly only post your questions in the chat window as of now. Thanks a lot. So Anil sir, you can go to chat window, go on to the questions, and you can answer the questions. Thank you.
And I would certainly like to, I said I like to make this session more interactive. That was my fundamental idea at the beginning. But unfortunately, because of this one-side communication, I have it's a one-way traffic now. But I would certainly, if I can, whatever questions you have, please be open to ask those questions, and I'll be more than happy to answer those questions. So I have some questions in front of me now. I will start answering one by one. The first question I saw, it was kindly note, how to evaluate source of harmonics. It's a very good question. See, what happens is, if you ask me, it's a very tricky question, or it's a tricky subject itself, finding the source of harmonics, because many times, the phase angle between voltage and current, when at the fundamental frequency, or phase angle between voltage and current at higher frequencies. For example, if you take a fifth harmonic current or a fifth harmonic voltage, there is a phase angle difference there also. Phase angle is used to compute the power flow. As you see, root 3 VLIL cos phi, which is a standard 50 cycle waveform. We use the root 3 VLI cos phi is the equation. So similar exercise, the cos phi stands for phase angle, correct? Cosine of the phase angle. You can use those phase angles and accordingly address the reactive power flow. So there are, but what happens is, if not the reactive, the harmonic power flow, sorry. The harmonic power flow you can calculate based on the phase angle, as I just told you. But if the harmonic current distortion is very small, then you cannot use this harmonic power flow basis, because the power flow will be very little. So you will not be able to easily identify. Again, see, harmonics is something which happens on a time domain. Depending on how the load is functioning, the load functioning multiple, see, with a single load connected to a grid, it's very easy to say which direction the harmonics is flowing. If you have multiple loads, all the loads are not working at the same sequence. So it's a very difficult exercise, even though some of the manufacturers say we can do this. But yes, if you are going to put multiple analyzers, as I said before, if you have a grid level, substation level, if you are going to put multiple PQ meters, and if you are going to do time synchronizing by using this GPS syncing, then you can always look at the relationship of flow or the phase angle at multiple nodes and come to the conclusions on which direction the phase angle go. The harmonic power flow happens. Yes, so I hope I answered this question. My simple submission is, there is no easy computation for calculating the source of harmonics, because the harmonic is a highly time varying function, and all these frequency domain calculations, phase angle calculations which you are doing, it's on a time domain, those calculations which are done on a frequency domain, it becomes a mismatch. So it's not easy to exactly predict. Yes, but you can predict it if you have multiple analyzers or meters installed at multiple points, and data is exchanged at a common place and evaluated the phase angles at multiple points, and see how the harmonics are flowing at multiple nodes, and you can come to a conclusion, yes, the source is here. But if you put one PQ meter or one PQ analyzer and trying to find out this, you may or may not be accurate in your calculation. You have certain way of, for example, if the reactive power, harmonic power flow is on the positive side or a negative side, as I just mentioned before, the 4-quadrant operation. According to that, you can say, yes, if the active, what happens if you're like in a solar plant, if you're generating and exporting power, power direction of power flow is on one direction. When you're importing the power flow direction in the other direction, because the phase angles are different. So similarly, harmonic generated on one direction or the other direction flow can be found out, but then it cannot be an accurate method. Okay, the next question is, is recording instruments for harmonics available now? DC transmission available in high voltage? Yeah, in fact, I explained about the harmonic analyzer that I just showed you about that PQ analyzer. We can use these sort of PQ analyzers, which are class A accuracy PQ analyzers, and you can look at all aspects of harmonics as well as other power quality problems. Yes, recording can be done. That class A analyzers are the best one, and you can have class A power quality meters also, which can be used as fixed units and use it for the purpose of measurements. So answer is yes, is available. What is the difference between a tuned and detuned reactor? Actually, when it comes to tuning and detuning, as I told you before, what happens is whenever you use a reactor, the reactor purpose is a certain amount of inductance. So now you have a capacitance in the network, and you have certain amount of source impedance in the network caused by the transformer and the upstream power line and the upstream generating source. All that produces source impedance at the point of connection. Now that source impedance, along with the capacitor load, when you connect it, there is a natural frequency, and that natural frequency, if it is nearer to the harmonic frequency, which I told you, like if it is a odd harmonic, third harmonic means is 150 cycle or 250 cycles. Now, what you have to do is, when you put a reactor, when you say tuning, you are tuning to a harmonic frequency. Now, if you have third harmonic current in a network, and if you want to filter the third harmonic current, then you tune the capacitor reactor to the third harmonic. That by tuning it, you are creating a circuit of capacitor with inductor tuned to 150 cycles, third harmonic current. Now, if you want to detuning it, you put a 14% reactor, then you detune it, the value away from the third harmonic current. That means it does not amplify the third harmonic current, it just protect the capacitor. So detuning means you are tuning it away from harmonic frequency. Tuning means you are tuning it at harmonic frequency so that harmonic currents are removed by tuning it. Detuning, you are not removing harmonics, you are only protecting the capacitor bank and avoiding a resonance. That is what the detuning is. Then the next question is, what is the permissible level of harmonics on both source and load? Yeah. Now, see, what happens is when you take a harmonic problem, the source impedance plays a very, very significant role in harmonics, because ultimately the harmonic sources are current sources. Harmonic is always produced as current. And when this harmonic current is flowing through the network, it produces voltage harmonics, because the network creates certain amount of impedance. So you have a voltage drop. And now, since this impedance is at harmonic frequency, the voltage drop also will be a harmonic voltage drop. So now the issue here is that, whenever you have harmonic source, the source impedance plays the game. And now IEEE 519 says that you can have certain level of harmonic voltage distortion. I was presenting in some of the slides that voltage harmonic distortion in a high voltage network can be 5%, but in a low voltage network, it can be 8%. Similarly, individual harmonic distortion on a high voltage network, when it's a high voltage up to 69 kV, I'm saying, above you have to go further down. So up to 69 kV, you can have voltage distortion, total voltage distortion 5%, individual voltage distortion is 3%. Similarly, if you take a low voltage, total distortion is 8%, individual is 5%. So harmonic voltage distortions are well defined in IEEE. But when it comes to current distortion, as I told you, current produced is dependent on the source impedance also. That means if you have higher short circuit level, higher ISC by IL, that means your source impedance is less. That means the drop in impedance is also less. That means you can generate higher harmonics. That is why when you go into IEEE 519 harmonic current distortion table, it tells you higher the ISC by IL, higher the distortion, total distortion you can inject into the network. So both current distortion and voltage distortions are well defined in IEEE, and I have covered it in the previous slides also. Nowadays, distributed generation being encouraged, do you think that whether it will have impact on power quality at LT network? Certainly, because distributed generation, fundamentally, if you are looking into all these renewable energy sources, which are variable renewable energy sources, I will call, because these renewable sources are not producing power at like normal generators. Because what happens, your network, when you take the network, is fundamentally having a rotary inertia, because all your power generating station, which are rotating turbines or rotating generators, rotating alternators, all these rotary generators produces a rotary inertia on the power network. Now when you bring in power electronic generating sources like a solar or a wind, which is again working based on wind, these are all variable output. So that means when there is a variable output or a power electronic output, the inertia of these devices does not match with the rotary inertia or the network itself. So there is a mismatch. Certainly, mismatch means it will reflect in terms of voltage fluctuation, frequency fluctuations, and power quality means. That means power quality. And again, harmonics also another problem which can be created by the power electronic devices because of the switching technology. Power electronic devices again operates at higher frequencies, so it can create other higher frequency noises also, which can, and as a higher frequency noises, it can, for a solar plant, can produce even higher order harmonics also. That means if you are carrying a power quality analyzer, which can only measure power harmonic up to 50 cycle, it may not record the harmonics produced by a solar plant. That could be in the higher order, maybe at the 60th order, 100th order. So that means you have to have a power quality analyzer which can possibly measure harmonic at least up to 140 or 150th order. So yes, distributed generation by solar, distributed generation by wind can create varying voltage output, varying frequencies also. So anyway, Mr. Jawahar, I think my answer to distributed generation, yes, it produces power quality, fundamentally frequency problems, voltage quality problems, and harmonic problems, as well as higher order harmonic problems. Not only lower order, third and 5 and 7 and 11, you can also have 140, 150th harmonic also produced by this. If active Mr. Prabhakaran, if active front-end filter produces higher order harmonics, will it not be more harmful than lower order harmonics? Exactly, it is. Because what happens is, in an active front-end drive, the front end of the active front-end drive is an inverter. So the purpose of using an inverter normally when you use any variable frequency drive, as I said before, it has a rectifier unit, it has an inverter unit. So in active front-end drive, you don't use a rectifier, you use IGBT. In the inverter, always in a conventional variable frequency drive, you are using IGBT on the inverter side, the diodes on the rectifier side. In active front-end, you use IGBT on both sides. Now the problem with IGBT, number one, is it is switching at a very high frequency. It is switching maybe at 16 kilohertz, 20 kilohertz. When it is switching at very high frequency, it produces very high harmonics also. Now, yes, the question is a very good question you're asking. It's harmful. It is harmful from two angles. Number one is these noises which can create a lot of noise related tripping of electronics, because many of your power controllers, many of your other, most of your control systems will have, clocks which works on a permanent 20 millisecond cycle. So you may end up multiple zero crossovers points when your active front-end drive is producing noises. So your controllers may misjudge it and it may operate and it can cause malfunction or it can cause accidents, number one. Number two, active front-end drives, when it's producing higher order harmonics, the higher order harmonics, when it is passing through the network. See, when you look at the network, for example, as I was telling before, when there's a lightning striking or when there is a capacitor bank switching, there is a certain amount of natural frequency of the network. It is just like a water flow. When the water is flowing and we suddenly stop the flow of water, there is a reaction by the flow, and the reaction is dependent on the dynamics of the water flow. Now here, the reaction towards a sudden jerk or a high is to immediately create a oscillating frequency. Now imagine a situation, if you have higher order harmonics flowing in the network, naturally most of the network natural frequencies are at the higher order frequencies. That means this higher order frequencies along with the system natural frequencies at the time of capacitor bank switching or at the time of a lightning can create a parallel resonance or a series resonance and increase your voltage substantially high. I had a case history with one of the metro stations in India where on a 33 kV, the voltage went up to 70 kV because of parallel resonance. And the source of this parallel resonance was a higher frequency harmonic current got amplified at the natural frequency of the network. So certainly there's it's harmful. Yeah, other question is, which system is quite useful for the grid HVDC or fax? Okay, see, we just discussed about in the first slides, I was talking about how you control the grid frequency or the grid voltage. Now, when you look into grid voltage, as I was saying, we need to do reactive corrections, reactive power corrections at the points where the loads are creating reactive power requirements are there. Now, in a network, active power flow holds the frequency properly. But a reactive power requirement at a load point, if you need a reactive power, you need a reactive power correction at the load. If you are going to send the reactive power from the generating station, naturally it causes voltage drop and more voltage instability on the network. So you put a capacitor bank. But the problem with the capacitor bank is these are all not flexible, devices which can operate on real time. Now, if you need a reactive power compensation at a much higher speed, like 160 microsecond, I told you before, then you have to go in for static compensation system or static VAR system. So yes, these are all called flexible AC transmission system devices, fax devices. So you need to use such StatComs or static VAR compensators when it comes to these sort of applications. Which system is quite useful for the grid, HVDC or fax? No, see, HVDC, I mean, you cannot compare HVDC. It's a fax device, no doubt, but HVDC is primarily used for large transfer of power. You bring it into DC and transfer huge amount of power from point A to point B. Unlike in a conventional transmission line, which can create a lot of drop in voltage, and again, as I told you, the grid stability problem. HVDC, you don't have that sort of a stability issues, unlike an AC systems are. So fax devices in HVDC is used, as well as fax devices are used also in the grid for real-time control of power factor correction and harmonic control, and we call static compensators or static VAR compensators for that. Now, I think this is a question of Jayanti. The question is lower order harmonic, especially third harmonic, is more dangerous than fifth and seventh harmonics? See, that way, all harmonics are dangerous if it is going to cause a resonance, fundamentally. Otherwise, harmonics can certainly have other effects, like it can overheat the transformer, overheat the motor, overheat the transmission line. Everything can get overheated by harmonics. So certainly any harmonics, the heat is ultimately, if you take a cable, the skin effect of the cable. When I say, when you have a direct current is flowing through the cable, the entire cross section of the cable is used as the area. That means the resistance of the cable is what? Rho L by A. If the cross section of area comes down, the resistance goes up. Now, what is skin effect? Skin effect is the effective area comes down in skin effect. That means higher order harmonics, when it is flowing through the cable, it is concentrating around the surface of the cable, thereby the resistance goes up. So that means if it's a third harmonic, fifth or seventh or 11th, whatever is the harmonics, the I squared R loss goes up very high. Now coming back between third, 5, 7, the third harmonic always flow through the neutral, because third harmonic is a 360 degree in symmetrical components. Third harmonic is a 360 degree vector. A fifth harmonic is a negative sequence vector. That means it rotates opposite to the RYB phase sequence. And the seventh harmonic is a positive sequence vector. That means seventh and fifth always flow through line. But third harmonic always come through the line and it adds up at the neutral and flows through the neutral. Yes, the third harmonic, what happens is it overheats the neutral. And many times, as you know, on the delta side of the transformer, third harmonic cannot flow in a delta system. Third harmonic always only, goes to the lines and it just sums up at the neutral. So there is no neutral in the delta system on a transformer. So naturally that harmonic tendency is to rotate inside the 11th primary side. So it overheats the transformer. Since it conducts through the neutral to ground, it overheats the neutral. So the bad effects of third harmonic is in terms of overheating transformer, overheating the neutral. The bad effects of fifth and seventh, it overheats the transformer, certainly it overheats the line, and if your grounding is not proper, it creates neutral to ground voltage also. That means 3, 5, 7, 11, everything is harmful. I would always say you should always maintain below the IEEE 519 limits, whichever is the harmonics. Higher order and the lower order, I think Chandra Muthuswamy, higher the harmonic order and lower the harmonic current, then why should we bother about higher order more than 50, as these values will be very meager? Good question again. See, Fourier transformation is used in full wave rectification. When you have full wave rectification, your fundamental equations, as I told you in the beginning, as that Fourier transformation equation, it starts with fundamental frequency of magnitude, let's say x. Then the next is third harmonic, magnitude x by 3. Then the next is fifth harmonic, magnitude x by 5. You are absolutely right. As higher is the harmonic frequency, lower is the magnitude of the harmonic. But all systems need not have to work perfect. You'll always have situations where there are, like the active front-end drive case, which we discussed just earlier. In those situations, there is no control in terms of how IGBT switching is taking place. You cannot bring in the concept of a perfect full wave rectification in the IGBT switching, because that operates at 60 or 8 kilohertz switching frequency. In those scenarios, your Fourier transformation does not hold good. Similarly, you take an arc furnace, you take an induction furnace. Those type of variable load also does not follow Fourier transformation. Only in Fourier transformation, you can say higher order harmonic is less in magnitude. But in reality, the loads are different, switching technologies are different. So you will have certainly different scenarios. So yes, that is why we also be concerned about higher order harmonics. And again, as I said in the earlier case, higher order harmonics can also create some amount of over voltages in the network, and that over voltage is called transient harmonics. Because any higher order harmonic, when it is flowing through the network, and since the network has a natural frequency, if a lightning strike on the network, or if there's a capacitor bank operated on the network, there is certain amount of switching, there is certain amount of oscillating frequency in the network. That oscillating frequency oscillates at the natural frequency of the network, which is determined by the capacitance and the inductance of the network, as you will know. Now, if you have higher order harmonics flowing through the network, this higher order harmonic can trigger a transient harmonics and create over voltage. So again, higher order harmonic can become dangerous there. So Fourier transformation does not hold good there also. There's Mr. Prabhakaran, there is another question that is about, is there any tune filter like detune filter? Similarly, is there any inactive filter opposite to active filter? I think all good questions, Mr. Prabhakaran. I think it says, is there any tune filter like detune filter? I think it's a very paradox type of a question. Let me try to understand. Is there any tune filter like detune filter? Detune filters, as I said before, is used for detuning a capacitor circuit so that the capacitor at fundamental frequency, it does the power factor correction. And when there are higher frequency passing through the network, the capacitor should be protected by detuning the capacitor by means of a reactor so that the capacitor does not amplify the harmonic currents. Now, if you say tuning means you have to tune that to any one of these harmonic, like fifth harmonic, seventh harmonic, it can be tuned. Now, there are passive variable tuned filters also. I think probably your question would have been directing to that technology of passive variable tune filters. See, this passive variable tune filters, uh, technically, if you ask me, it's a very complex design. And the other thing is that, when it comes to, when you have beautifully working active harmonic filters, which can work perfectly well as a broadband filter, it can filter your integer harmonics, your non-integer harmonics. When I say non-integer, in the harmonics. That means odd, even, inter, subharmonics, super, all these harmonics, when a passive filter, active filter can filter out, going for a variable tune passive filter may not be is economically there will be a benefit, but on a long term, on a life cycle cost wise, active filter will be still better. But variable tune passive filters, again, selectively, all solutions, whether it's passive solutions or active solution, has to be decided based on the application. For example, if you ask me, there are wonderful passive solutions for harmonic mitigation. There are concept called neutral current eliminator. It's a zigzag transformer concept, which is used in filtering third harmonic current. What it does is you install this zigzag transformer on the neutral to ground. It has a zero sequence combination. It works in such a way that when a third harmonic current flows, it has a zigzag design so that the fluxes oppose each other and it negates the harmonic current. So that's a passive solution. You can also have passive filtering in terms of harmonic mitigating transformers, where you use this converter transformers or phase shifting transformers, where you do 50 degrees, 30 degree phase shifting. That can also be a good solution case to case. There can also be mitigation done by passive, we call it passive broadband filters. These filters are used at the input of a VFD. For example, instead of going for an active front-end drive, which can be more expensive, you can use this broadband passive filter. The advantage is that broadband passive filter filters all the harmonics produced by the drive, number one. Number two, it also don't allow any noises to come from externally and destroy the electronics of the drive. So broadband passive filter, again, an application-based choice. So yes, when it comes to passive filters, whether it's a detune filter, tune filter, passive phase shifting transformer, or a neutral current zigzag transformer, or whether it's a broadband passive filter for VFDs, all these concepts are also equally good. But you have to see the right application. That is, a power quality has to be understood in its totality, and then come out with a beautiful, good solution for that. I believe that your question was addressing towards those variable tune passive filter. Variable tune passive filter also can be a good solution, but again, an application choice. Other question, which was, is there any inactive filter opposite to active filter? So it is like an antibody to, I have not certainly come across any inactive filter, that terminology, but see what happens with active filter. Active filters are fundamentally used for harmonic mitigation, phase balancing, and power factor correction. Now, in a factory, if you want to do all the three things, balancing loads, because many times you will see RYB phases are not balanced properly, and sometimes you will see there is power factor, leading power factor problem. Sometimes you see active harmonic problem. So active filters can take care of all the three things. Similarly, if the MVR requirement goes higher and higher, for example, a normal active harmonic filter, we can use up to 300 amps. Then if you want 500 amps or 1000 amps, then you put parallelly up to 18 filters you can connect in parallel. But that is a very expensive choice. That is why static compensation systems are all come. Yes, other higher end, the elder brother of active harmonic filter is StatComs. So otherwise, an inactive filter, probably I may have to discuss over the phone. I couldn't understand your question correctly to explain beyond this. Then the other thing is Aditya Gana, I think Aditya, sorry, I used the first name, Aditya. In substations, I see capacitor bank switching on off as per LDC for power factor correction. And during that instant, in dedicated HT feeders, many electronic panel failures were reported by industries. What is the solution? Yeah, I think this, the whole, it's a very good question, because you have really addressed some of the presentation slides of mine. And naturally, when power factor correction is done, it causes over voltage. It causes whenever you use capacitor banks for on a transformer, you have to always make sure that the transformer voltage rise under light load should not go more than 2%. That means whenever you put a KVR, X amount of KVR on a transformer secondary, you have to make sure that there's a mathematical computation. I can share that detail through our through TecKXpert itself. With that calculation, you can decide how much KVR you can safely put on a transformer so that it does not cause over voltage. And now, this coming back to this power factor switching, yes, power factor switching creates over voltages. It can create oscillatory over voltages, and because of that, the electronic cards can fail. The question is, electronic panel fail were reported by industries. I would certainly say many times the electronic cards are not something which is subjected directly to the power line. Your fundamental power frequency AC equipments are all basically strong against some of these fluctuations, but the electronics are not as sensitive as that. So many times I would say the electronic card failure you can address by proper grounding, bring the right reference voltage, and make sure that the neutral to ground voltage shift is minimized. Because many times if the grounding is not proper, any incoming voltage surge, even a oscillatory surge, can increase the neutral to ground voltage, and that neutral to ground voltage, how the electronic system is grounded in this network, can cause a failure of the electronic card. So I would rather say the best way is to analyze the waveform. We should put a harmonic power quality analyzer and capture the waveform. Number one. This is all where the permanently fixed power quality monitors can help, because this fixed power quality monitor can continuously record waveforms and tell you whether there are any waveforms which are causing any problem to the electronic card. For example, today, when you use this fixed PQ meter or a harmonic analyzer, there is something called ITIC graph. ITIC graph is a graph which plots on a XYZ, which tells you what is the voltage envelope for a sensitive electronic device. So this, when you plot this ITIC graph using PQ analyzer or PQ meter, it tells you how many over voltage incidents happen in that particular location, above the tolerance level, how many happen within the tolerance, how many happen below the tolerance, and what was the magnitude of those events, what was the duration of those events. So the ITIC graph then plots a scatter plot which tells you how many events were tolerated and what was the waveform of each event. Everything ITIC graph with a good PQ analyzer, you can do that. Once you do that, you will know what is the nature of the voltage surge or an oscillation that is happening in that facility. And then we can see with the analysis what is the neutral ground voltage happening there. With that, you can see whether the grounding is not done properly, and then you can solve it. I would say if it is a over voltage, put transient protection like transient voltage surge suppressors, but do the grounding check the neutral to ground voltage, check the incoming voltage current, see whether how the over voltage or transients are behaving by capturing on the waveforms, and then take the transient over voltage if it is over voltage, select a suitable surge arrestor, install it near to the electronic cards, and you can protect that. There is, again, when you put surge arrestors, there is a coordination you have to do, just like this type 2 like in the fuse coordination or a breaker coordination, you do even surge arrestor, you have to do a coordination exercise. Don't put just a surge arrestor at a transient over voltage, TVSS close to the victim load like that. You have to scale it up and decide what is the rating and all that. So surge suppressor, effective grounding, but do it after taking a proper measurement. That is the way I would answer that question. And then Sri Devi. This is Sri Devi is a question. The load is near with the even the load is near the distribution transformer, but voltage fluctuations are there. How to minimize it? Even the load is near the distribution transformer, but voltage. See, that's what the voltage fluctuations are. We have to see where the voltage fluctuation. What is the cause of the voltage fluctuation? Is it because the grid level? How strong is the grid? That is why I said earlier, if a short circuit level and all that matters at the point of coupling. If the grid level, if it's strong, then your voltage will remain stable. Whatever is the type of load you connect, if the grid is strong, the voltage is not going to be distorted. It will still remain as a strong body withstanding virus. But then if the system is weak, any load connected can create a current quality problem. When there is a current quality problem, that means when there is a distortion in the current waveform, if the source is weak, the voltage also get distorted. So here in this particular case, my answer to this question is that we should see what is causing this voltage fluctuation, and then we can see how to minimize it. So I would rather say we have to use a good PQ analyzer and capture this waveform, and then we can see what is the cause of the waveform, and then we can find a source to minimize the waveform. Certainly, it is possible. We can minimize it by measuring it. And as I told you, most of the cases, grounding is a very important thing. Never look at grounding as a small subject, because grounding is like the platform on which the building is built. Now, the whole power system is built on a poor grounding. The entire power system will collapse, because any voltage surges, harmonics, and or voltages, all this thing will badly affect your neutral to ground voltages or your electronics unless the grounding is done properly. So then the next question is, where need to be connect power quality analyzer and tap changer? Yes. See, when you connect a power quality analyzer, all power quality analyzers should be connected. For example, if you are doing a root cause analysis, here you are saying it's a tap changer. You should then, when you connect a PQ analyzer, the point one where you should put a PQ analyzer is always near to the victim load. Which is the victim? Is the on-load tap changer is the problem area? Certainly, you have to connect this at the primary of the transformer or the secondary of the transformer, depending on the on-load tap changer, and then see by the analyzer how the voltage is fluctuating. Because when you have an on-load tap changer, certainly you can see the voltage waveform fluctuation. And from the voltage waveform fluctuation and current waveform fluctuation, you can pinpoint and say whether the OLTC is switching happening properly, or whether there is some arc is happening while switching. This means, yes, by putting a PQ analyzer near to the OLTC, whether it's secondary or the primary, that voltage point you should put it, because that is where the tap changing taking place. You should also put this at the source point also, because you cannot only depend on the victim load alone. We should also go to the source. So in situations like this, you should measure simultaneously one PQ analyzer at the point of coupling or at the upstream, and one PQ analyzer at the downstream where the OLTC is functioning. During high wind generation, grid voltage profile reduces drastically. High wind generation, grid voltage profile reduces drastically. So whether WEGs are operating in quadrant 4, if so, what are remedial measures to be taken in TNEB side? See this, now that 4-quadrant operation, you are really bringing some relation to that slide. Certainly, this I would say, I don't know whether you have done a power quality measurement, because some of this question, when you say grid voltage profile is changing, naturally a wind generator is a variable power source. It is not like a constant generator of a hydro plant or a thermal plant or an atomic power plant or anything, because there the voltage is stable, power output is stable. And but in a wind generation or solar, your voltage profile all gets affected by the power output. As I said in the initial slides, the voltage. So, and also there will be a reactive power issue also, because voltage profile can also be influenced by that. I would rather say, if you can put an analyzer and even a 4-quadrant, if the analyzer can exactly tell you which direction the reactive power is flowing, how the waveforms are looking at that point of flow. Everything can be captured by the waveform. So that is why, see, for electrical engineers, I would certainly say that when we do power quality analysis, I know harmonic analysis, everybody has substantially done such analysis, but then nobody has looked at the waveform analysis. It is just like, using an ECG of your heart. The heart functioning, by looking at the ECG, you can the doctor exactly say whether the heart functioning is correct. As electrical engineers, ultimately, it is all voltage and signals what they are using in ECG also. So similarly, if you have a PQ meter which can capture the waveform, then we can analyze the waveform and find out what is the cause of this voltage profile variation. It could be 4-quadrant related reactive power flow, or it could be even the active power issue also. Or it can be something to do with some unbalance also. So that means when you do a measurement only, you can clearly find that. And then we can certainly solve this. I'm 100% sure this is a solvable problem. Very interesting, sir. Okay, thank you for that comment. Ms. Jayanti's reply. Mr. Chandran, wind generators and solar inverters are tested for their harmonic levels in their factory. without influence of higher harmonic demand from the load end. Exactly. See, that is the problem. Today, power electronic devices and variable renewable energy sources are going to be one of the biggest challenge when it comes to grid operation. Okay, as I said, that is why I use those first slides. I really wanted to have had an interact. I used those first 5-6 slides to have a good interactive session with all of you. But unfortunately, we couldn't do that interaction. That is the only purpose I use those first slides, because you, as power engineers, you will know the importance of frequency control and voltage control. So yes, now coming back to this question, wind generators and solar inverters are tested for the harmonic level. See, look at what happens about these wind inverters also. When it takes a solar inverter, it's an IGBT. As the active front-end drive story we just discussed before, it produces electromagnetic interferences because it produces higher order harmonics and high frequency noises. So when you go with solar inverters, it is not just the harmonics. See, you generally use a PQ harmonic analyzer, which cannot measure beyond 50th harmonic. 50th harmonic is only 2.5 kilohertz. That is 50 into 50 is 2500 hertz. Now all the solar inverters, active front-end drives are producing harmonics which is more than 3000, 4000, 5000 hertz. So how do you measure this with a harmonic analyzer which can only up to measure up to 50th harmonic? So some of these areas are, yes, when you say tested the harmonic levels in the factory, I don't know when they tested the factory, what sort of testing they're doing also. Are they testing what is the level of electromagnetic emission it is causing? And what is the level of harmonics it is producing? I don't know. As you rightly said, when it is connected to the grid, yes, in the grid level, one aspect is a climate aspect, and the second aspect is how the grid network behaves, and the third aspect is as the load connected depending on where the load is. If it is nearer to these generators, yes, the impact of the load also comes. Otherwise, in a strong network, if the voltage is strong, then the sort of nonlinear variable renewable energy sources can work on those stable voltage networks. Okay, one is this national grid concept, which we are going in for. Perhaps national grid can be one solution towards managing these sort of variable renewable energy sources. But coming back to your question, I would certainly say that yes, harmonic levels at the factory, what analyzers they use for that? Did they check EMI levels? That is higher order harmonics. Did they check the noise levels? And then without the influence of higher order, question is once again how wind generators and solar inverters are tested for their harmonic levels in the factory. Yes, wind generators testing, I'm not an expert on that, so I cannot make much comment on that. But when it comes to power quality, whatever, whether it's a wind generator or a solar inverter at the factory level, when they're testing, make sure they're using Class A analyzers, number one. That is 61004-30 Class A analyzers. And number two, make sure that analyzer can do waveform recording so that you exactly know at the time of testing how the waveforms are behaving. So you can always compare that waveform vis-a-vis the waveform at the field level. So this is how you can get the actual baseline data. Then of course, when it comes to the scenario, when you connect to the load, measure the load also. See, ultimately, if you do all these measurements and collect the waveforms, any problem in power system we can address. All power problems can be handled by power quality analysis, no doubt at all. I would rather say, if I can have a little more information on this question, then I can probably throw more lights. Second one is it possible to calculate ISC by IL for all the high tension consumers like TNEB? So many parameters are required to calculate ISC, IL at low consumer and any EC method. It's an absolute question. I mean, that is what, if you look into IEEE 519 has brought this ISC by IL concept, and it has really caused even the point of coupling itself, whether you have to measure at the TNEV point of coupling or you have to measure at the output of the transformer secondary itself is a debate when it comes to IEEE 519. If you go by IEC goes by more by absolute current. So even G54, that is the British standards, none of them uses ISC by IL basis. The ISC by IL I would say ISC by IL can be an easy method if you know exactly the short circuit level at the point of coupling. Now what happens, majority of the consumers, they must be having a transformer or a high voltage or a low voltage switchgear, and they take the design value. For example, if they have 40 kiloampere LT panel, or if they have a 25 kiloampere 11 kV panel, they consider that 25 kA or that 50 kA of the LV as the short circuit level, which is wrong. And then they calculate that, and full load current, of course, 1 year electricity bill, you can calculate your average full load current, maximum demand load current. But then that ISC, if you go by the ISC rating by the by the design value of the equipment, it is wrong. The actual ISC short circuit level, you need to probably have a very extensive power system analysis done, or your own probably, since your operations team must be doing load flow studies and fault level studies and KVR flow studies. I'm quite sure that this data of actual short circuit at the point of coupling should be available, from your simulation or your operations team itself. Otherwise, IEEE 500 is a very tricky subject. That is why in IEC, they don't use this ISC by IL basis. They go by absolute, the permitted absolute current, which can be, which is there at the point of coupling. So if you go by those bases, it's very easy to, bring the regulation. ISC IL is a very tricky subject, and ISC short circuit level, no consumer will know the short circuit level. If you go to a consumer, he will say, my LV panel is 50 kiloampere, so that is the short circuit level. But if you have to check up with your own operations, your team, and check what is the load flow studies and all that done, and on a real-time basis, if your load dispatch center or a control room can tell what is the short circuit level at that point. Again, this short circuit level can be, depending on if it is already a impedance, if the network is more or less fixed, the short circuit level will not change much. But otherwise, if you are bringing more transformers, some new generators, again it will change. But it's not that it will happen every day basis. So I would rather say that data you should take from your own operations team. The next question is how to choose 4.4, 7% and 14%. See, now, as I said in one of the previous slides, if the percentage is nothing but if you have certain amount of harmonic, that is a question from Chandran. If you have certain harmonics in the network, let's say third harmonic, fifth harmonic, seventh harmonic. Third is the lowest odd harmonic that you can find in any network, provided the networks are all using the right type of VFDs or LEDs and all that. When I say right type, the full wave rectification should be taking place so that you can pinpoint and say the harmonics are 3, 5, 7, 11 and all that. Now, when you're going for this 4.4, 7%, 14% detuned reactors, the 4.4 and 7% is more or less the same. Because I would say don't worry too much about 4.4% because this 4.4% is used in Europe. The reason is that 4.4% comes very close to 189 hertz. So a 7% is 210 hertz. So in Europe they use ripple frequency around 180 hertz. So they generally don't use 7%. They use 4.4. So in Indian context, you don't have to look at 4.4 at all. You should only use 7%. So the basis of selection is that if you have a lot of LED computer loads, that I said single phase electronic loads. I gave a presentation at the beginning that is NP plus minus 1. The characteristic harmonic of a single phase electronic load starts with number 3 because it has 4 diodes, so it is 4 plus minus 1. 3, 5, 7, 11. If you have a 3-phase electronic load, it has a 6 pulse. It has 6 diodes in 3 phases. So that means it starts at 5. 6 plus 1 minus 1. So 5, 7, 11. So if you have a lot of lighting loads, third harmonic currents, your lot of computer loads, then you have to go for a 14% reactor. A 14% reactor will detune your circuit below the third harmonic current. Third harmonic current is 150 cycle. When you detune below 150, it is detuning at 135 hertz. So at 135 hertz, you are detuned, so no harmonic will get amplified. Similarly, in the system, if you don't have any third harmonic, if it start only with fifth, if you are only substantially third harmonic, VFDs, UPS and all that, there you use a 14% detuned reactor. There, 14% detuned reactor is at 189 hertz. That means it's again away from 250 cycles. That means what you have to do always is the detuning frequency should be always below the harmonic frequency. Now, if you have a network is having third, 5, 7, 11, then you detune it below 3. That is below 3 is 135. And coming back to 4.4, how to choose is that you have to basically see if the system has a lot of third harmonic, then you have to choose 14%. If the system is having more of fifth harmonic, then you use 7%. Don't go by the 4.4% because 4.4% is not relevant to the Indian scenarios. Okay, there are a lot of sales talk will go on, but as a technical person, I don't say 4.4 is a wrong thing, but 7% or 4.4, both are the same. That is how I count it. Other thing is Gujarat. I will. Okay, I think thank you all. I think, is it possible to measure? Is it possible to measure, record the harmonics in energy meter at consumer end, like energy meter? I don't think energy meter you cannot do the harmonic measurement, because energy meters are efficiently doing energy accuracy. Those aspects are there. So your question was, is it possible to measure and record the harmonic in energy meter at consumer, like energy? If your question is relating to smart meters and all that, smart meters have can also take handle some power quality data. But the issue here is that smart meters are fundamentally used for revenue purpose. So the power quality standard is IEC 61000-4-30 Class A. Some smart meters are not certified under IEC 61000. So I would rather say any harmonic measurement should be done by PQ meters or PQ analyzers, so that you have the right algorithms used in the computation. See, end of the day, IEC 61000 recommends you certain algorithms, for computation of harmonics, computation of voltage sag, computation of swell. There is a certain algorithm used. So in a smart meter or energy meter, you don't have all that. So you don't end up with the right value. So I would say energy meter, conventional, there are a lot of multifunction meters which give some harmonic data, but these are all not according to the IEC 61000 algorithms. So I will never recommend those sort of things. Another question from Dr. Balamurugan is that the utilities go, a very great eye-opener session for the utilities. Thank you, sir. To levy more penalties who inject more harmonics. In turn, the utility should maintain the quality. Smart metering may address the monitor this in delivering quality power supply. So I think smart metering, smart metering certainly has certain sampling frequency, like 124 samples per cycle. But a power quality meter do sampling at 516 samples per cycle. So you can imagine the level of the accuracy with which a power quality meter capture power quality data is much higher than a smart meter data. Number one. Number two, a smart meter brought whatever is the waveform and whatever is the data transfer from the smart meter. You use the data transfer capability or the bandwidth of smart meter to efficiently look at the energy aspects. And your protection relays also can do some PQ metering. I would say whenever you take a grid level power quality, you should use a combination of power quality meters, protection relays, and revenue meters, and some of this data. That is the one software I was presenting before, PQView, one database software. You bring this multiple data to a common database, and then you use this data in the right way to interpret power quality problems, so that your decisions are right. When it comes to revenue metering, your decisions will be right. When it comes to PQ, your decision will be right. But smart meters for PQ function, I won't say it is, yes, it can give you some PQ data, but the efficiency, the application, again, as I said, 61,000 classification is also done for PQ meters, not for smart meters. Yes, it is very important that PQ power quality is addressed by the utilities, because as I present the first slide, 6% GDP. I think that is today, to fight a pandemic like COVID, the country is struggling with a 10% GDP. I think as power engineers, I think we should address power quality far more seriously and make the consumers who are causing power quality problems penalized for their problem, and make the utilities, the voltage also equally stable, so that, and make the manufacturers who are making spurious materials, they should follow standards. That means it's a joint activity of manufacturers, end users, and the power provider. And I would certainly say the time has come to address power quality in a far more serious way, so that our nation GDP growth and our nation's growth itself, can be enhanced by reducing the cost on power quality. Some of the quick questions. Thank you, sir. I think I have a lot of thanks. I keep telling thanks from my side also, but I'm so sorry that you cannot interact. Two identical nonlinear loads, one connected to a weak source and the other strong. Is it fair to insist the customer connect to the weak source to install filter for no fault of him? Excellent question. Yeah, I think that is what the answer to the earlier question, because ultimately voltage quality is to be maintained by the grid operator. And to ensure voltage quality is good, the grid operator should ensure the customers are not polluting the grid. So you penalize the customers who are polluting the grid. But certainly coming back, whether you ask me whether if he is producing harmonics, whether it is weak source or strong source, if he is producing harmonics and if it is violating the IEEE norms, certainly he should be, it is also his fault, because there is, we can't say that my voltage source is weak, so this poor fellow, I will not penalize it, because you have to make sure he also obeys the standards. He should buy the equipment which does not emit harmonics and other electromagnetic interference problems. That means he should buy equipment which follows the standards. He should also ensure if the harmonics are above what is mentioned at the point of coupling, you should put filters also, so that the grid can become stronger. And if everybody does it, your voltage will become much stronger. And then in future, they need not have to put a filter. If your grid becomes stronger, then some cases you don't have, the guys don't have to put filter, because you already have a strong voltage. So you can tell the consumers, irrespective of whatever the quality of your current, my voltage is remaining stable, so you can do. But at this point of time, you have to certainly ask him to put the filter. So what is the way forward? How power utilities can improve this harmonics better with renewable and power electronics being future? How can consumers, especially ST consumers, can contribute to improve harmonics? How can we fix the onus to improve harmonics? I think the CEA, latest CEA regulation, which has come out on 2018, August 2018, is very clearly mentioning the need to do continuous power quality monitoring. I would say that the question is from Aditya. My answer here is that ST consumers should install power quality meters. This has been done abroad. Most of the ST consumers are putting power quality meters, and they should transfer the data online to the utility so that you know which ST consumer is causing problem. I think the answer to this again is the way forward is insist on continuous PQ monitoring. Let them install PQ meters at the point of coupling, and let the regulation what CE has announced, let get implemented in a way so that nobody causes power quality problem on the grid. Point of coupling, yes, point of common coupling is a next question from Michael Raja. The IEEE 519 defines point of common coupling as a point where in the grid, in the substation, for example, TNEB is supplying power to X number of customers. At the substation where all these X number of customers are coming and joining, that is a point of common coupling. That means wherever you have a bus, in that bus, you are feeding a consumer A. And if a consumer B is also fed from the same bus, then the point of common coupling is that the bus. But then, many times you have to also go down to the consumer, because as I said before, the short circuit level and all those issues are there. So you have to also go to the consumer point. I think IEEE 519, the recent 2014 amendment, they have shifted the point of common coupling to the primary side of the transformer, from where the utility is feeding power to the grid. So I would say IEEE 2014 defines point of common coupling at the point where the utility is supplying power to the consumer. Then the next question is, active front-end are vulnerable with supra harmonics. How can we suggest active harmonic filters, as these are also high-speed switching with IGBT? Active harmonic filters, yes, it also works on IGBTs. I don't say IGBTs are harmful. IGBTs are required for high-frequency switching. Even HVDC uses IGBT. Everywhere IGBTs are used. But the issue with IGBT is that it also produces electromagnetic interferences. So when you go for an active front-end buyer, when you buy that, he has to comply the electromagnetic EMI emission standards has to be complied by him. That means when somebody is supplying an active front-end drive, it should ensure that he is putting proper LC filtering at the input of active front-end drive, so that no higher order harmonics or noises are coming from the IGBT side to the primary, to the source side. Similarly, when it comes to solar inverters, even LEDs, even the LEDs produce a EMI. So what the LED guys do, they also put an EMI filter. So I think the answer to that question is EMI filtering is required. Even active harmonic filter is IEC compliant for harmonic emission. So IGBTs can be used as long as it complies to IEC emission standards. Good evening, sir. In the inverter, we are using high switching frequency to reduce the TSD. When TSD reduces, the switching loss will increase across the switch. How do you reduce the harmonic and switching loss in inverter? Yes, that's a good question again. See, what happens today in IGBT technology, you have something called 3-level topology and 2-level topology. The 3-level topology uses a higher number of, it uses about 6, I think it uses about 3 layers of IGBT switching. I mean, if you go into the, and by using 3 layers and compared to 2-level, you are reducing the switching losses, the heat losses, the energy losses, and increasing the life. Because in a 2-level, that IGBT is getting stressed to much higher voltages. In a 3-level, you are reducing the voltage stress by series connecting more IGBTs in series. So 3-level technology is the solution. 3-level topology is the solution to that question from Gauri Shankar, that by using 3-level topology, you can bring down this switching losses as well as energy loss in the active filter, as well as noise from the active filter also. Good. HVD, in HVDC system, please explain your views on. See, in the HVDC also, certainly harmonics are produced because anywhere power electronics are used, certainly it's a source of electromagnetic interference and high frequency noises and harmonics. So if you look at the HVDCs, the HVDCs also come with harmonic filtering. HVDC systems, you can see the filters also goes as a part and parcel of the HVDC, because when you're converting AC to the DC, prior to transferring on HVCD transmission line, there is harmonics produced at the source point. So filters are used there to ensure that HVDC, the actual, when you convert AC to DC, that transfer point, the filters are used. So yes, that is taken care. Supramani, thank you all participants. Okay. What is your opinion on putting static energy meters in the system, whether it will produce harmonics? The static energy meters will certainly, static energy meters producing harmonics and all that, in a small level, I don't think it can be a problem. It is all about how you design the static energy meters so that, the emission levels are brought down. Particularly when 3-phase solar generation is connected, that is another issue. A 3-phase solar generator is connected to the LT. How can we control the PQ in the grid system? Any monitoring? See, I would rather say, anything, if you control, you can, if you certainly, you can measure it and solve these problems. I would say majority of the questions which I come across, it's all about, solvable problems. But then if you can measure it, then we can solve it also. That is how I'll answer this, because I know the time factor is getting reduced. So I would rather, I'll wait for a call from I don't see any more questions on this. I don't see any more. I think these are all the questions I see. If anything is missed out, yeah. Hello.
Yeah, thank you a lot, sir. I think that's a what do you say, wave of questions coming your way, and the way you answered is really highly appreciable.
Thank you.
I think I will now wind up the session. I would request Prabhakaran sir to give a vote of thanks and the closing comments, please.
Okay. Yeah, it's a lot of questions. In fact, unfortunate that, this whole couldn't be interactive. Then otherwise we could have addressed all these questions. Anyway, it's okay.
So
okay.
You can stay on the call, sir.
Yeah.
Sir, can you please give us a vote of thanks? Thank you.
Okay, sir. Good evening once again to all of you. It is like a calm after storm. 2.5 continuous hours of session with unchanged energy level, starting from the basics, accelerating to the top.
Thank you, sir. Thank you.
Covering all minor points, chapters in between it. It is a complete package of knowledge imparting, sir, regarding harmonics.
Thank you, sir.
Amazing effort, and we are really astonished about our energy level without losing iota of interest throughout the session. Sir, actually at the start I mentioned harmonics as an allergy subject. Now after 2.5 years, I get a feel that I must correct myself in converting it from the allergy subject to an attractive subject. It is quite evident from the barrage of questions which makes this session as a huge hit. On behalf of all participants and TNB friends of our family, I think I thank very much Mr. Anil sir once again Mr. Murugesan sir, very dynamic, ever dynamic.
Thank you, sir.
Sir, the wonderful team of expert team who
Thank
has
you, sir.
made a tremendous effort in making this session very master session, very useful, very organized, very methodological, and very informative.
Great, sir. Thank you.
Thank you.
Thank you, sir. Yeah, thank you, sir.
Yeah.